In the vast silence of space, most stars live quiet lives. They burn steadily, gently radiating light for millions or even billions of years. But among them, there exists a rare kind of star, one that refuses to play by the rules. P Cygni is one such cosmic rebel. It doesn't just shine, it erupts. It doesn't merely exist, it declares itself. Where other stars fade calmly into the tapestry of the universe, P Cygni flares with dramatic bursts, like a storm unwilling to pass. Imagine looking up into the sky and suddenly noticing a new star that wasn't there before, so bright, it could outshine everything around it, and then slowly watching it dim again over months and years. That was the story of P Cygni in the year 1600, when it first caught the eye of astonished astronomers. But that was only the beginning. But before we continue, subscribe to the channel so you don't miss out on any of these videos. This isn't just the tale of a flickering point in the sky. P Cygni is a cosmic engine of chaos and beauty. It pulses with inner violence, shedding its outer layers in vast eruptions of gas and light. It has baffled astronomers for centuries and continues to challenge everything we thought we knew about the life cycles of massive stars. The very idea that a star could change so drastically in real time was unthinkable in the early days of astronomy. Yet here was P Cygni, refusing to sit quietly in the catalogue of stars, rewriting its entry with every outburst. This isn't just a star, it's a spectacle. P Cygni doesn't merely shine, it performs. It is loud in a language of photons and particles, throwing tantrums of radiation that can be seen across vast interstellar distances. Some stars whisper their final days with a quiet fade. P Cygni shouts. For centuries, it has burned with the urgency of something running out of time, or perhaps building towards something even more explosive. Its pattern of sudden brightening followed by a slow dimming has become a signature, a sign of inner turmoil that gives us clues into its volatile nature. And while it has quieted since its great outburst centuries ago, it hasn't truly settled. It's like a sleeping giant, restless in its slumber. Even now, P Cygni experiences smaller eruptions, mass loss events, and changes in brightness. It's a ticking time bomb in astronomical terms, alive, unstable, and full of secrets. To observe it is to watch a slow-motion explosion unfold over centuries. This is the story of a star that refuses to stay quiet. A star that blazes against the stillness. A star that continues to shake the fabric of stellar theory. Welcome to the life, the rage, and the cosmic poetry of P Cygni. P Cygni is unlike most stars we know, not just in how it behaves, but in what it is. Classified as a luminous blue variable, or LBV, it belongs to one of the rarest and most volatile classes of stars in the universe. These stars are not only incredibly massive, but also incredibly unstable. They live fast, burn bright, and often die in the most dramatic of ways. Just the term, luminous blue variable, evokes images of something both brilliant and erratic, a searing, unstable flame fighting against its own collapse. Luminous blue variables are among the brightest stars in the galaxy, often shining hundreds of thousands to even millions of times more brightly than our Sun. But their brightness isn't constant. They shift. They pulse. They erupt. And P Cygni is a textbook example, perhaps even the prototype, of this extraordinary stellar category. What separates these stars from their calmer cousins is their violent tendency to lose mass through extreme stellar winds and giant outbursts, often shedding material into the surrounding space in vast clouds of gas and dust. In doing so, they carve out nebulous structures around themselves, shaping their own environment like sculptors working in plasma and radiation. P Cygni sits about 6,000 light-years away in the constellation Cygnus, and even at that distance, it's bright enough to be seen with modest telescopes. Its blue hue reveals its immense surface temperature, estimated to be around 18,000 degrees Celsius, far hotter than the Sun. But what really makes it stand out isn't just the heat, the mass, or the light, it's the instability. This star is constantly teetering on the edge of balance. The gravity trying to hold it together is at war with the immense pressure from the radiation inside trying to blow it apart. Every pulse, every eruption is a skirmish in that internal battle. LBVs like P Cygni represent a fleeting phase in the lives of the most massive stars. They don't remain in this state long, perhaps just tens of thousands of years, a blink in cosmic time. And that makes observing one especially valuable. We're watching a stellar transformation unfold in real time, a moment in a star's life that is as rare as it is spectacular. P Cygni, with all its instability and drama, is a case study in stellar volatility, helping scientists decode the mysteries of high-mass stellar evolution. It is not just another star to catalog and forget. It is one of the few windows we have into a process so brief and rare that even among the billions of stars in our galaxy, only a handful are caught in this act. P Cygni is burning through its life with ferocity, leaking mass into space, evolving under our gaze. It is a volatile masterpiece in motion, and the universe has given us front-row seats. P Cygni's story doesn't begin with modern science. It begins in the age of telescopic dawn, long before astrophysics, long before spectral analysis, when a few patient observers gazed skyward and noticed something strange. In the year 1600 AD, long before the nature of stars was understood, P Cygni burst into view with startling brilliance. It was not a subtle change. Suddenly, where once there was nothing visible to the naked eye, a new star appeared in the northern sky, bright enough to demand attention. The event was so remarkable that it was recorded by Willem Janssen Blauw, a Dutch astronomer and cartographer. He noted a new star in the constellation Cygnus, describing its appearance with care, unaware that he was witnessing the first documented outburst of what we now call a luminous blue variable. Blauw's observation wasn't just an entry in a journal. It was the beginning of P Cygni's place in astronomical history. This single flare-up in the night sky marked it as one of the earliest recognized variable stars ever recorded by humanity. Over the following years, P Cygni faded from naked eye visibility, as mysteriously as it had arrived. But the echo of that moment lingered. Other astronomers followed up with occasional observations, noting that this strange star did not behave like others. It didn't stay constant in brightness. It waxed and waned. And slowly, the understanding dawned that P Cygni was a variable star, not because it moved, but because its brightness changed with time. This was an extraordinary idea for the era. Stars were supposed to be fixed and unchanging, celestial constants in the heavens. But P Cygni shattered that illusion. What makes this history even more fascinating is that it occurred during a pivotal moment in human understanding of the cosmos. Just a few decades earlier, Copernicus had challenged the geocentric view of the universe. Galileo would soon turn his telescope toward the stars. And into this whirlwind of discovery, P Cygni flared like a cosmic exclamation mark, an unpredictable, radiant burst from the heavens that said, in effect, "You don't know everything yet." The eruption of 1600 wasn't just a singular spectacle. It was the opening act in a much longer and more mysterious tale. In the centuries that followed, astronomers began to notice that this was no ordinary star. It had a tendency to change. Not with the predictable pulses of Cepheids, or the eclipses of binary systems, but with chaotic eruptions that signaled powerful internal unrest. The 1600 eruption became a reference point, not just for P Cygni's behavior, but for the broader understanding of stellar variability itself. Today, we know that what Blauw observed was likely one of P Cygni's major mass loss events, a colossal shedding of its outer layers into space. That event marked the beginning of our recorded relationship with the star, anchoring it in both astronomical records and historical significance. In many ways, P Cygni was not just a variable star. It was a star that helped define what variability in stars could mean. It turned out to be more than a curiosity. It became a benchmark, a mystery, and a legend, wrapped in glowing plasma and ever-shifting brightness. In the grand tapestry of stellar evolution, most stars follow a relatively steady path, forming from clouds of gas and dust, burning through their fuel in predictable patterns, and fading away in quiet, calculable ends. But then there are the outliers, the stars that burn too hot, too bright, and too fast. These are the cosmic heavyweights, the giants that live in extremes, defying the norm with their size, luminosity, and behavior. And among these titans, an elite and incredibly rare subclass exists, the luminous blue variables, or LBVs. P Cygni is one of them, not just a member of the group, but an archetype of the category itself. Luminous blue variables are among the most massive and luminous stars known, their surface temperatures often ranging between 10,000 and 25,000 Kelvin. Their brightness can exceed that of the Sun by factors of hundreds of thousands, or even into the millions. To even begin to comprehend that is to imagine an object so radiantly powerful that it dominates the energy output of entire star clusters. They're like cosmic bonfires surrounded by mere candles. But this brilliance comes at a price: stability. The sheer force of their radiation pushes outward against their own gravitational pull, constantly threatening to tear them apart. And often it does. The name, luminous blue variable, is more than a description, it's a forecast. These stars shine with a brilliant blue-white light due to their high temperatures, but they are unstable by nature, prone to enormous variability in both brightness and spectral characteristics. Unlike regular variable stars that pulse in defined, rhythmic ways, LBVs experience massive and often unpredictable changes in brightness, sometimes brightening by multiple magnitudes over months or years before fading again. And accompanying these changes are powerful mass ejections, where vast shells of gas and dust are blown into space. These outbursts are not gentle stellar breezes. They are eruptions, violent, dynamic events that can shed solar masses of material into the surrounding interstellar medium. During such episodes, an LBV can lose an amount of mass equivalent to the Sun's entire mass over a short geological time span. The most massive LBVs are shedding their lives into space, one violent gasp at a time. LBVs typically spend only a few tens of thousands of years in this phase, an eye blink in the lifespan of a star. This fleeting nature adds to their mystery and importance. Because they are so massive, their entire life cycle is compressed compared to less massive stars. They form quickly, evolve rapidly, and often die in cataclysmic explosions. But the LBV phase is particularly rare and poorly understood, largely because few stars are ever observed in it. That's why each LBV, especially one as historically significant and closely studied as P Cygni, is a scientific goldmine. LBVs occupy a fascinating spot on the Hertzsprung-Russell diagram, a graphical tool used by astronomers to categorize stars based on their brightness and temperature. These stars are found near the upper left, in the most luminous and hottest part of the chart. However, during outbursts, they can temporarily shift positions, moving along complex paths as their outer layers expand and cool. This movement complicates our understanding of stellar evolution because it defies the steady patterns we observe in most other stars. In fact, some theorists argue that the LBV phase may be a transitional state, a brief way station between the main sequence and the supernova finale, or possibly the Wolf-Rayet phase for the most massive stars. But what causes these stars to become so unstable? That remains one of the biggest mysteries. One leading theory involves the so-called Eddington limit, the point at which the outward pressure from radiation equals the inward pull of gravity. When a star approaches or exceeds this limit, its outer layers can no longer be held in place, and the result is a massive outflow of material. This instability can be exacerbated by internal opacity changes, turbulent convection, and even binary interactions if the star has a companion. There's also a fascinating hypothesis that some LBV eruptions might be linked to failed supernova events where the star tries, but fails, to completely collapse, instead expelling some material and surviving to shine another day. This idea is still under active investigation and has major implications for our understanding of the final stages of stellar life. Despite their rarity, LBVs have been instrumental in challenging our assumptions about how stars evolve and die. The most famous example is Eta Carinae, a massive LBV in the southern sky that underwent a spectacular eruption in the 1840s. During that event, Eta Carinae became the second brightest star in the sky, visible in broad daylight for weeks. It expelled an estimated 10 to 20 solar masses of material in a single event, creating the now iconic Homunculus Nebula. Eta Carinae's violent behavior has been studied extensively, and it bears remarkable similarities to P Cygni, both in brightness changes and in the spectral fingerprints of mass loss. These kinds of explosive events are thought to play a critical role in galactic ecology. The material ejected by LBVs doesn't just vanish, it enriches the surrounding space with heavy elements like nitrogen, carbon, and oxygen. These elements are the building blocks for new stars, planets, and ultimately life itself. In this way, even as they destroy themselves, LBVs seed the galaxy with the raw ingredients of creation. They are at once agents of chaos and architects of the future. P Cygni's place within this class is unique. While other LBVs have undergone enormous eruptions and returned to obscurity, P Cygni has remained relatively steady since its great eruption in the 1600s, with smaller outbursts occurring over the centuries. Its persistence in this state, neither exploding nor fading, offers astronomers a continuous laboratory to study the delicate balance between gravity and radiation in massive stars. It is one of the few LBVs that we can observe over long timescales, tracking its changes with precision and depth. The very term, luminous blue variable, owes part of its definition to the observations of P Cygni. When the classification was formalized, it was this star's behavior, its brightness changes, its spectrum, its outbursts, that helped define the criteria. In this sense, P Cygni doesn't just belong to the LBV class. It helped create it. Every subsequent LBV discovered is compared, in some way, to the strange and mesmerizing behavior of this ancient blue giant. What makes the LBV class so compelling is that it represents a phase of ultimate transformation. These stars are shedding the very mass that defines them, altering their futures with each pulse. Some may become Wolf-Rayet stars, bare cores stripped of their outer hydrogen layers, before finally collapsing into black holes. Others may skip intermediate stages altogether and explode as hypernovae or instability supernovae, leaving behind only questions and radiation. The LBV phase is the last chaotic breath before an end that may be unimaginably violent. And in that light, every flicker, every eruption of a star like P Cygni becomes part of a story far bigger than itself. To watch a luminous blue variable is to witness instability at a cosmic scale. It is to stand at the edge of stellar life and feel the breath of dying giants, to see energy and mass entangled in battles that rewrite the laws of matter and motion. P Cygni is not simply a bright star. It is a phenomenon, a blueprint of destruction and rebirth. And within its glow lies a portrait of impermanence, painted in hydrogen and heat, across the face of the galaxy. Unlike the calm, predictable rhythms of many stars, P Cygni pulses with a different kind of beat, an erratic, sometimes explosive dance of light that hints at the turmoil simmering beneath its luminous surface. To an observer watching across decades or centuries, P Cygni appears not as a static beacon, but as a living, breathing entity. Its brightness changes in peculiar, often violent ways, driven by events so extreme they challenge our understanding of how stars behave. This is not a case of simple variability. P Cygni's light fluctuations tell the story of a massive star in conflict with its own physical limits, a celestial titan pushing itself to the edge. Since its dramatic eruption in 1600 AD, astronomers have tracked these changes with increasing sophistication. The star has never fully returned to the invisibility it once held before that eruption. Instead, it has remained faintly visible to the naked eye under dark skies, with a relatively constant baseline brightness, yet embedded within that constancy are periodic variations. These aren't the kind of predictable pulsations one finds in Cepheid variables, nor are they the mechanical eclipses of binary stars. P Cygni's changes are chaotic and asymmetrical. Sometimes it brightens gradually, other times suddenly. Sometimes it fades rapidly, only to stabilize for years. Each fluctuation tells us that something deep within the star is stirring. Modern photometric observations have revealed a pattern of long-term, low-amplitude variations in its light curve, gentle waves punctuated by occasional bursts of heightened activity. These events aren't just surface-level flickers. They are the result of colossal structural rearrangements within the star. When P Cygni brightens, it's often because it has expelled a layer of its outer envelope, an eruption that sends material hurtling into space and temporarily increases the star's apparent luminosity. In many cases, this brightening is caused not by an actual increase in intrinsic energy output, but by the expanding photosphere becoming cooler and larger, shifting its light output toward the visible spectrum and thus appearing brighter to our eyes and instruments. This process of brightening through expansion and eruption is characteristic of luminous blue variables. But with P Cygni, it's especially intriguing because the star has displayed this behavior intermittently for centuries without tipping over into complete collapse. It's as though the star flirts with disaster but always pulls back just in time. The cycle can be thought of as a kind of stellar breathing, an inhale of growing internal pressure, a pause at the brink, and then an exhale of matter and light as the star vents its excess energy. What's particularly unusual is that after its initial outburst in 1600, P Cygni did not simply stabilize and quiet down. Historical records indicate that the star underwent a series of smaller outbursts in the years that followed. For instance, secondary brightenings occurred around 1655 and 1665, each accompanied by minor fluctuations in brightness and changes in its visual magnitude. These smaller events, while not as dramatic as the first eruption, were still significant, evidence that the star was continuing to lose mass and undergo internal changes. In more recent times, high-resolution monitoring has shown that P Cygni's variability continues, albeit on subtler levels. Observations using photometry and spectroscopy have confirmed micro-variations, tiny changes in brightness on the scale of hundredths of a magnitude. These variations are thought to be the result of pulsations within the star's outer layers, possibly connected to instabilities in its radiation-driven winds or changes in internal convection. They may also reflect brief interruptions in the equilibrium between the star's outward radiation pressure and the gravitational force holding it together. There is an important distinction to make here. Not all brightness changes in P Cygni are necessarily visible as dramatic events. Some are slow and drawn out over decades, requiring careful measurements to detect. Others are more abrupt, tied to discrete episodes of mass ejection that produce shockwaves in the stellar atmosphere. The key point is that P Cygni's light is never entirely at rest. Even when the changes are imperceptible to the naked eye, the star is still simmering beneath the surface, building toward its next release of energy. The mass loss events associated with these brightness changes are staggering in scale. During outbursts, P Cygni has been observed to shed material at rates exceeding 10 solar masses per year. To put that in perspective, that's more than 30 times the mass of Earth being ejected annually. Over centuries, this steady and punctuated loss has stripped away vast quantities of the star's outer layers, surrounding it with expanding shells of gas that glow faintly in infrared and radio wavelengths. These shells serve as historical markers of the star's past convulsions, cosmic scars left behind by centuries of upheaval. One particularly fascinating aspect of P Cygni's brightness pattern is the delay between ejection and dimming. After a major mass loss event, the star can remain in an inflated, brightened state for years or even decades before cooling and contracting slightly. This delayed reaction contributes to the irregularity of its light curve and makes it difficult to predict future behavior. It's like trying to forecast volcanic eruptions by watching clouds, possible, but fraught with uncertainty. Adding to the mystery is the fact that despite all this activity, P Cygni has never gone completely dark again since its 1600 flare-up. It has hovered around a magnitude of 4.8 to 5.0 in recent centuries, meaning it is still faintly visible under ideal conditions. This enduring visibility is itself strange. Most stars that erupt so violently tend to either fade into obscurity or progress rapidly towards supernova. Yet P Cygni lingers in a strange limbo, seemingly trapped between its past violence and its inevitable fate. This in-between state might offer a clue about the deeper mechanisms driving its variability. Some researchers propose that P Cygni is locked in a quasi-stable phase, where the star is continuously adjusting to the mass it has already lost, trying to find a new equilibrium. Others suggest that binary interaction may be a factor, possibly with a hidden companion contributing to periodic disturbances, though no conclusive evidence of such a companion has been found. Whatever the mechanism, the result is clear: P Cygni's brightness is not a stable trait. It is a dynamic process, a living waveform of light sculpted by eruptions, contractions, and stellar weather on unimaginable scales. Each flicker and fade is a message from the interior of a star more than 30 times the mass of the Sun, expressing itself through radiation and motion. And we, perched on a distant planet in a quiet solar system, have the privilege of watching that message unfold over centuries. P Cygni's unusual brightness pattern stands as one of the most compelling puzzles in astrophysics. It suggests a stellar object caught in a prolonged act of transformation, a creature of fire and force, fighting its own gravity with every outburst. Unlike other stars that burn quietly in the night, P Cygni narrates its life through dramatic episodes of change. To monitor its brightness is to eavesdrop on a conversation between mass and energy, between collapse and expansion, between stability and annihilation. It's a celestial performance that spans generations, and the curtain has not yet fallen. One of P Cygni's most defining scientific signatures, a trait so unique that it bears the star's very name, is not just in its light or its brightness, but in the shape of its spectral lines. When astronomers peer into the star's spectrum using powerful instruments that dissect starlight into its component wavelengths, they find something remarkable, a distinctive pattern that reveals exactly what's happening in and around the star. This spectral fingerprint is known as the P Cygni profile, and it has become one of the most recognizable indicators of strong stellar winds and mass loss in massive stars. At first glance, a star's spectrum looks like a rainbow with specific dark or bright lines at precise locations, each line corresponding to an element absorbing or emitting light at a particular wavelength. These lines act like a barcode, allowing astronomers to decode a star's composition, temperature, and even motion. But in the case of P Cygni, this barcode has a unique and highly informative twist. The P Cygni profile appears as a combination of two distinct features in the spectral line of an element, an emission peak and a blue-shifted absorption trough. In other words, you get a bright line where the gas emits light, and just beside it on the blue, short wavelength side, a dark line where light has been absorbed. This pairing creates an asymmetric line shape that tells a complex story of dynamic processes surrounding the star. To understand why this happens, imagine the star enveloped in a vast, spherical shell of gas, a stellar wind that is being expelled into space at tremendous speed. Now, consider how light interacts with this outflowing gas. As light from the star passes through the shell of moving gas, atoms in the wind can absorb some of that light, especially from the part of the wind moving toward us. Because that gas is rushing outward, the absorption gets blue-shifted. The Doppler effect shifts the wavelength of the absorbed light to a slightly shorter value. This creates the characteristic absorption trough on the blue side of the line. Meanwhile, the gas that's not directly in the path of the star's light, particularly the gas around the sides, can emit light in all directions. This leads to the emission component of the spectral line, which typically appears at or near the rest wavelength of the transition being observed. The result is a line profile that rises on the red side and dips on the blue side, a marker of a star that is not just glowing, but flowing. This spectral profile was first observed in P Cygni in the 19th century, and it was so distinctive, so emblematic of stellar winds, that it became forever associated with the star. Since then, the term P Cygni profile has been adopted widely in astrophysics. Whenever astronomers see this particular shape in the spectrum of another object, be it a massive star, a nova, or even an active galactic nucleus, they know that outflows are present. It's a universal symbol of matter in motion. In P Cygni's case, these profiles appear prominently in lines from hydrogen, especially H-alpha, helium, and various ions of heavier elements like nitrogen and iron. Each of these elements traces gas at different temperatures and densities, giving astronomers a detailed, layered picture of the wind structure around the star. By analyzing these spectral features, scientists can estimate the velocity of the outflow, which in P Cygni's case is about 185 km per second, or roughly 400,000 miles per hour. That's enough to carry stellar material from the surface out into interstellar space in just a matter of days. Even more remarkably, the strength and shape of these profiles can vary over time, allowing astronomers to track the evolution of the stellar wind and detect subtle changes in the mass loss rate. Sometimes the absorption component becomes deeper, signaling a denser or faster outflow. At other times, the emission peak brightens or shifts slightly, hinting at fluctuations in temperature or turbulence in the wind. These changes don't just help us understand P Cygni, they help us understand massive stars as a whole. And the P Cygni profile doesn't just exist in visible light. It can also appear in ultraviolet and infrared wavelengths, depending on the energy levels involved and the sensitivity of the instruments being used. Observatories like the Hubble Space Telescope and ground-based high-resolution spectrographs have used this phenomenon to probe not only the outflows of P Cygni itself but of stars all across the galaxy and beyond. It has become a diagnostic tool as fundamental to stellar astrophysics as redshift is to cosmology. The importance of this spectral signature cannot be overstated. It provides a direct, observable link between what we see from Earth and what is physically happening in the atmospheres of massive stars. It confirms that P Cygni is losing mass at a dramatic rate, and that this loss is not uniform, but a chaotic, often accelerating process. And because light carries the imprint of these outflows across space and time, even stars that are far too distant to study in detail can be partially understood through their spectral echoes. P Cygni's profile represents one of the earliest and most striking examples of spectroscopy as a window into stellar behavior. Long before we could image stellar surfaces, long before we could simulate their turbulent interiors with computer models, we had this profile, an encoded signature of violent winds and powerful forces. It allowed early astronomers to infer the invisible, to hear the roaring winds of a star with their eyes, and to build a foundation for the study of stellar evolution. And even now, centuries after that first eruption in 1600 and over 100 years since the profile was first documented, P Cygni continues to whisper to us through its light. Every spectrum taken is a snapshot of a dynamic, shifting environment, a record of the star's breath, its rage, its resilience. In the precise language of light and absorption, the P Cygni profile reminds us that stars are not static points in the sky. They are living, evolving, and sometimes, if we know how to look, communicating in brilliant and turbulent tongues. Understanding that a star like P Cygni is exploding, again and again, not in a single cataclysmic end but through repeated convulsions of energy and matter, requires more than just looking at it through a telescope. From Earth, we see a point of light in the sky. That point can flicker, shift slightly in brightness, maybe change in color if the variation is extreme. But if we want to know why it's flickering, if we want to peer beneath that shimmering facade and uncover the violence unfolding inside, we must rely on something deeper, the tools and techniques of modern astrophysics. And that means two key things: light curves and spectral analysis. When astronomers track P Cygni over time, they don't just record its brightness as a single number. They monitor it continuously, recording its magnitude across various wavelengths day after day, year after year. These values are then plotted to form a light curve, a graph that shows how the star's brightness changes over time. At first glance, this might look like just a series of bumps and dips on a line. But to a trained observer, each irregularity in that curve is a clue, an echo of some internal change, an outer layer ejected, or a pulse of radiation breaking free from the star's core. The light curve of P Cygni is not neat or symmetrical. It does not show periodic regularity like a pulsating star. Instead, it undulates in chaotic waves. There are slow, gradual increases in brightness that can span years, followed by sudden drops or brief dimming events. Sometimes the star will seem stable for decades, then unexpectedly grow slightly brighter for a few months before returning to baseline. These curves tell a story of a star that is never truly at rest. Every rise and fall is a flare of stellar instability, a sign that deep within, something has shifted. What makes this data even more powerful is that it can be correlated with spectral changes. While light curves tell us when something is happening, spectra reveal what that something is. By spreading the star's light into its component colors and analyzing how the absorption and emission lines change over time, astronomers can infer massive changes in the star's atmosphere and surroundings. For example, during one of P Cygni's mass loss events, the blue-shifted absorption lines in its spectrum become deeper or shift in position, signaling that gas is being blown outward from the star's surface at tremendous speeds. These outflows, reaching hundreds of kilometers per second, leave their signature in the form of Doppler-shifted features, precisely the same P Cygni profile we explored before. When these features become more pronounced or start appearing in additional elements, such as helium, nitrogen, or iron, it tells astronomers that new material has been ejected, and at different temperatures or velocities. In some cases, astronomers also detect broadening of spectral lines, another sign that the gas around the star is becoming more turbulent. Broader lines can indicate higher temperatures, increased pressure, or more chaotic motion in the gas, hallmarks of a star in the midst of an eruptive event. The combination of broadening, shifting, and changing line strengths is like a symphony of physics playing out in real time. It's not just theory, it's evidence. Even more revealing are the changes in ionization states seen in the spectral lines. During an eruption, the shock wave from the ejected material heats the surrounding gas to extreme temperatures. This causes atoms to lose electrons and become more highly ionized. So, instead of just seeing lines from neutral hydrogen or singly ionized nitrogen, astronomers may suddenly observe lines from triply ionized atoms. These transitions require enormous amounts of energy and are a clear sign that something explosive has taken place. The appearance or disappearance of such lines across time can be directly linked to outbursts and the energy dynamics of the star's outer layers. But the story doesn't end there. As ejected material cools and drifts away from the star, it can form dust, or scatter light, or become ionized again by ongoing radiation. All of these phenomena leave secondary effects in the spectrum, such as infrared excesses or emission in forbidden lines that typically appear in low-density, shocked gas. By observing the spectrum not just in visible light, but across the electromagnetic spectrum, from ultraviolet to infrared, astronomers build a complete picture of what's happening around P Cygni in 3 dimensions and across time. There are also occasional detections of polarization changes in the star's light, which further hint at asymmetry in the outflow. If the star were simply expanding and contracting symmetrically, we wouldn't expect its light to become polarized. But small changes in the orientation or shape of the ejected shells, perhaps influenced by rotation or unseen companions, can cause the light to scatter in ways that leave behind a measurable signal. These measurements are subtle, but they reveal that P Cygni's eruptions may not always be spherically uniform. They may come in waves, arcs, or plumes, adding further complexity to the story. One particularly fascinating method astronomers now use is spectroscopic time series analysis, taking high-resolution spectra repeatedly over long periods and mapping how each spectral line evolves. With this method, scientists can detect not just the eruptions themselves, but the lead up to them, tiny shifts in velocity, subtle deepening of absorption, slight asymmetries in the profile. These are the stellar equivalents of seismic tremors before a volcanic eruption. They provide early warnings, helping us understand how instability builds inside such massive stars and when it might break the surface. And then there's the matter of multi-wavelength imaging, which complements all of the above. During particularly violent events, the ultraviolet and X-ray output of the star can spike, evidence of shock heating in the outer envelope, or in regions where ejected material collides with older shells. Space telescopes like Hubble and Chandra have captured images of the surroundings of P Cygni, revealing faint arcs and knots of glowing gas that represent earlier eruptions still expanding through space. These are visible remnants of past explosions, cosmic fingerprints of a star that keeps rewriting its own history. All of these methods, taken together, show us with crystal clarity that P Cygni is not a passive object. It is erupting. It is shedding its skin in stellar convulsions, throwing its outer layers into space one breath at a time. And unlike a supernova, which explodes in a single, world-ending flash, P Cygni is unfolding its destruction over centuries, letting us witness the slow-motion collapse of a star far too massive to die quietly. Each observation we make of P Cygni, each dip in the light curve, each twitch in the spectrum, is another page in the diary of its demise. We know it's exploding because it tells us so, not in words, but in radiation, velocity, and change. And if we continue to watch closely, we may yet catch the moment when these preliminary convulsions give way to something final, a supernova, a hypernova, or perhaps something even stranger. On clear nights in the northern hemisphere, when the summer air begins to cool and the skies open wide above forests and fields, one constellation often dominates the zenith, Cygnus, the swan. Gracefully spread across the Milky Way like a bird in mid-flight, Cygnus is a beacon in the night sky, rich with stars, nebulae, and deep sky wonders. Within its wingspan lies a legendary star, faint to the naked eye but famous in the annals of astronomy, P Cygni. Locating P Cygni begins with finding one of the brightest and most recognizable stars in the northern sky, Deneb. Deneb forms the tail of Cygnus the swan, and is also a key point in the Summer Triangle, a prominent asterism that includes the bright stars Vega and Altair. Deneb is a brilliant, bluish-white star of its own renown, a supergiant glowing some 2,600 light-years away. Just to the southeast of Deneb, embedded in the dense star fields of the Milky Way's spiral arm, lies the more elusive P Cygni, nestled between the stars Gamma Cygni and Eta Cygni. Though not bright enough to command attention like Deneb or Vega, P Cygni is certainly visible with a good pair of binoculars or a small backyard telescope. Its magnitude hovers around 4.8 to 5.0, making it just visible to the naked eye under very dark skies, especially when the moon is absent and light pollution is minimal. But what makes P Cygni remarkable isn't its prominence in the night sky, it's what it represents, a star that is both ancient and active, both quietly glowing and cosmically roaring. To a casual stargazer, P Cygni might appear as a typical, faint point of light among many. But to astronomers, its precise position in RA 20 hours 17 minutes and 47.2 seconds, Dec plus 38 degrees 1 minute 58 marks a kind of celestial observatory. That location in Cygnus is more than coordinates, it's a window into stellar evolution, a time capsule from 6,000 light-years away. When you look at P Cygni, you're not seeing the star as it is today. You're seeing it as it was 6,000 years ago, because that's how long its light has taken to reach Earth. Back when ancient civilizations were just discovering agriculture and astronomy, P Cygni was already sending out the photons you now receive with your eye. Cygnus itself is a constellation steeped in mythology and cosmic splendor. In Greek legend, the swan was often associated with Zeus or Orpheus, depending on the tale. But beyond myth, Cygnus is a true treasure chest for modern astronomy. It contains not just P Cygni and Deneb, but a host of other famous objects, like the North America Nebula, NGC 7000, the Veil Nebula supernova remnant, and Cygnus X1, one of the strongest black hole candidates in the Milky Way. In fact, the position of P Cygni within this stellar neighborhood makes it even more compelling. It's surrounded by interstellar material glowing with the energy of past eruptions, and it lies in the galactic plane where the density of stars and gas is highest. This cosmic traffic zone enhances the visual richness of its surroundings. Observers using long-exposure photography or high-powered instruments often catch faint traces of the gas shells that P Cygni has thrown off in its violent past, expanding ripples of light and matter that are now colliding with the surrounding medium. As the Milky Way arches across the sky like a shimmering ribbon, P Cygni holds its place, fixed among a billion shifting points of light. It doesn't move rapidly across the heavens like a planet, nor does it blink out like a transient nova. It simply burns and breathes, dimming and brightening with ancient rhythms. For millennia, it has watched over this corner of the sky, and in doing so, become one of its most enduring and enigmatic residents. There's something deeply poetic about knowing that a star so violent, so dynamic, resides within such a serene and graceful constellation. The swan, gliding across the river of the galaxy, hides within its wings a star that is anything but calm. If Deneb is the gleaming plume of Cygnus' tail, then P Cygni might be its burning heart, pulsing, struggling, evolving before our eyes. For amateur astronomers and professionals alike, pointing a telescope at P Cygni is a kind of pilgrimage. It's a quiet reminder that even in the stillness of the night sky, change is always happening. Beneath that pale dot lies a storm, a star casting off its outer layers, creating echoes that ripple through space and time. And all of this unfolds from a single, seemingly unremarkable point of light in the northern sky. So the next time you stand beneath the stars and trace the shape of Cygnus among the Milky Way's haze, take a moment to find Deneb. Look just a little to the southeast, into the denser patch of galactic light. There, amid the whispers of ancient gas clouds and stellar dust, lies P Cygni, the quiet star with a violent soul. The story of P Cygni truly erupted, both literally and historically, in the year 1600, when this previously unremarkable star suddenly made itself known to the world in a brilliant, unexpected display. It was not discovered through the lens of modern science, nor with the aid of space telescopes or digital instruments. Instead, its arrival came during a time of great astronomical awakening, when human eyes scanned the heavens for omens, patterns, and signs from the divine. And what they saw then would mark one of the earliest recorded instances of a massive stellar outburst, catching the attention of sky watchers across Europe and beyond. In the summer of 1600, P Cygni erupted in a way that could not be ignored. Prior to that, it had gone unnoticed, either too faint to be seen or simply blending into the rich background of the Cygnus constellation. But suddenly, seemingly without warning, it grew brighter, dramatically so. At its peak, it reached about magnitude 3.0, easily visible to the naked eye and far brighter than the surrounding stars it had previously hidden among. For the first time in known history, this mysterious star had stepped onto the stage of human observation. One of the earliest records of this event comes from Dutch cartographer and astronomer Willem Janssen Blauw, a student of the renowned Danish astronomer Tycho Brahe. Blauw meticulously noted the appearance of this new star in the constellation Cygnus, describing its brightness and position. Unlike a typical nova that brightens once and fades away, P Cygni displayed strange behavior. It fluctuated in brightness. After its initial eruption, it faded, only to brighten again in subsequent years, notably around 1655 and 1665. This on-again, off-again luminosity bewildered observers of the time, many of whom lacked the vocabulary or understanding to explain such erratic behavior. What made the 1600 eruption especially noteworthy was the sheer scale of it. Modern astronomers, reconstructing the event through historical records and physical modeling, estimate that during the outburst, P Cygni may have expelled a staggering amount of material, possibly more than a tenth of a solar mass. That's more than 30,000 times the mass of the Earth thrown violently into space in a relatively short period. This eruption didn't just brighten the star, it fundamentally transformed it. The expelled gas expanded outward, forming a glowing shell that even now continues to drift away at hundreds of kilometers per second. Today, faint traces of this ancient outburst can still be observed in infrared and radio wavelengths, like the fading smoke of a long-cooled fire. In the context of astronomical history, the eruption of 1600 was profound. It occurred only decades after the invention of the telescope, during a period when the idea of change in the heavens was still controversial. The prevailing Aristotelian belief held that the stars were fixed, eternal, and perfect. Supernovae and variable stars challenged that idea, but each event required careful documentation and philosophical reevaluation. P Cygni, by suddenly brightening in a familiar part of the sky, became a key data point in the evolving understanding of the dynamic universe. The timing of its discovery was fortuitous in another sense as well. The 17th century marked the dawn of scientific astronomy, with new tools, new methods, and new minds eager to explore celestial phenomena. While P Cygni's behavior was confusing to early observers, it also inspired deeper scrutiny. Over the next few decades and centuries, astronomers continued to monitor its brightness, noting that although it never returned to its pre-eruption faintness, it also never stabilized into a steady state. This persistent variability planted the seeds for future classifications, eventually contributing to the modern understanding of luminous blue variables as a distinct class of massive, unstable stars. What makes this historical outburst even more fascinating is that it may not have been the first time P Cygni had flared into brilliance. There are speculative suggestions, based on nebular structure and expansion velocities, that similar eruptions may have occurred even before 1600, perhaps centuries earlier, unseen or unrecorded by human eyes. If true, this would place the 1600 eruption not as an isolated anomaly, but as part of a longer, more complex pattern of eruptive behavior that spans centuries or even millennia. It's as if P Cygni has been screaming in slow motion across time, and the 1600 flare was simply the first scream loud enough to reach us. In a way, the outburst of 1600 serves as both a birth and a revelation, the moment when P Cygni emerged from anonymity and declared its nature to the cosmos. It was not a steady burning star like our Sun. It was a behemoth on the brink of transformation, tearing itself apart in cycles of furious light. And this first documented eruption gave astronomers the earliest opportunity to witness a massive star in the throes of self-destruction, not in a final supernova, but in a slow, erratic collapse of its outer layers. Centuries later, with advanced instruments and theoretical frameworks, we now understand much more about what likely happened. Deep inside P Cygni, the balance between radiation pressure and gravity became unstable, causing the star's outer envelope to expand rapidly. As that material was ejected, it briefly made the star's surface larger and cooler, shifting its radiation toward the visible spectrum and making it appear dramatically brighter. Then, as the gas thinned and cooled, the brightness faded, until the next surge built up, and the cycle repeated. What we observed in 1600 wasn't just a star getting brighter. It was the visible symptom of a profound internal struggle, a titanic battle between the forces that hold a star together and those that threaten to blow it apart. It was the first modern glimpse into the heart of a luminous blue variable, a harbinger of more discoveries to come. Today, astronomers look back at that eruption not only as a historical curiosity, but as a foundational moment in the study of stellar instability. The 1600 outburst turned P Cygni into a natural laboratory, a living case study of mass loss, stellar winds, and variable luminosity. It remains one of the longest monitored massive stars in the galaxy, and its story began, truly, on that fateful night when the world first noticed it shining with unnatural brilliance. A star that had slumbered in the background for millennia chose that moment to roar. To gaze at P Cygni is to witness a star in a prolonged act of self-destruction. Not the sudden, dramatic finale of a supernova, but a slow, thunderous unraveling, like a mountain that crumbles and quakes and avalanches long before its final collapse. Yes, P Cygni is dying. But its death is not a singular moment. It's a process stretched across centuries, a drawn-out battle between the forces keeping it intact and those trying to tear it apart. P Cygni is a massive star, and massive stars live fast and die young. Unlike our Sun, which burns steadily over billions of years, stars with 20 or 30 times the Sun's mass burn through their nuclear fuel at a reckless pace. The very same gravity that pulled so much gas together to form them also squeezes their cores more tightly, raising the internal temperatures and forcing fusion to proceed faster. This high-energy lifestyle comes with a cost: instability. And P Cygni is the embodiment of that instability. Its repeated eruptions and irregular brightness aren't signs of a thriving star. They are symptoms of exhaustion. When stars like P Cygni enter their post-main sequence phase, they begin to run out of hydrogen in their cores. This disrupts the delicate balance between gravitational collapse and radiation pressure, the tug-of-war that allows a star to maintain its structure. As hydrogen is depleted, the core contracts and heats up, sparking fusion of heavier elements like helium, carbon, and beyond. Each new fuel source produces energy for only a brief time, and each shift throws the outer layers into chaos. In P Cygni's case, this internal unrest manifests as violent outbursts, moments when the pressure becomes too great, and the star violently ejects part of its outer envelope. These are not polite, gentle puffs of gas. These are powerful, high-velocity winds capable of blowing away entire solar masses of material over time. With every eruption, P Cygni loses mass, and that mass is crucial. The star is literally flinging away the very matter that keeps it from collapsing. The outer layers we see, the shimmering, turbulent envelope of gas, are thinning. The more mass it loses, the less radiation pressure it can sustain to push back against gravity. Eventually, this balance will tip. The core will continue to shrink, grow hotter, and march through the periodic table, fusing elements in quick succession until it reaches iron. And once it hits iron, fusion stops. That's the wall every massive star crashes into. Fusion of iron doesn't produce energy, it consumes it. The core collapses. The star dies, not slowly this time, but in an instant. P Cygni, then, is not merely variable. It is terminal. Its eruptions are not random quirks. They are the star's way of prolonging the inevitable, of relieving internal pressure before it boils over. Each eruption buys it a little time, but only a little. Every burst is a heartbeat closer to collapse. Every outflow is a breath in a terminal sigh. What's remarkable is how long this death has taken. Since the Great Eruption of 1600, P Cygni has remained in a kind of unstable limbo. It hasn't settled back into calm, but it hasn't yet reached the climax of its existence either. It's stalled in a critical evolutionary stage, hovering near the brink of the wolf-rayet phase, or perhaps already entering it quietly. This is the stage where a massive star has lost most of its hydrogen envelope and begins to expose its hot, fusion-powered core, blasting even stronger winds and shedding even more material. Eventually, whether tomorrow or in 10,000 years, P Cygni will run out of tricks. Its core will no longer be able to support the weight of its own gravity. The moment iron accumulates at the center, collapse becomes inevitable. In the blink of an eye, the core will shrink to the size of a city and rebound in a shockwave that tears the star apart. The result? A supernova, likely of type 2 or even type Ion, given the massive amount of surrounding material from centuries of prior eruptions. This will not be a quiet event. It will be visible across galaxies. The remnants of P Cygni will light up the interstellar medium, forming a nebula glowing with the echoes of its last breath. And what of its core? If enough mass remains, the final collapse may form a black hole. If not, it could become a neutron star, an ultra-dense sphere of matter spinning at incredible speed, possibly emitting pulses of radiation as a pulsar. Either way, what exists today as a flickering point in Cygnus will become a stellar corpse, forever transformed by the process it's now enduring. Some may wonder, if it's dying, why does it still look so alive? Why, after 4 centuries, has it not yet detonated into its grand finale? The answer lies in the scale of cosmic time. For humans, centuries are long. For stars, they are but moments. The slow death of P Cygni, stretched over hundreds or even thousands of years, is still just the final breath in a life that began millions of years ago. And the fact that we're alive to witness it, at this precise stage, when the eruptions have begun but the end has not yet come, is a profound stroke of timing. To study P Cygni today is to read the final chapters of a massive star's autobiography, with each eruption a paragraph, each spectral shift a sentence. It is not a question of if P Cygni will die, but when. And as the star continues to stagger toward its inevitable fate, astronomers remain vigilant, recording its convulsions in the hope of catching the moment it crosses the point of no return. This is the slow death of a giant, not a whisper, but a series of roars echoing through space. When a star like P Cygni erupts, it isn't a simple or uniform process. It's the violent, turbulent consequence of deeply rooted instability inside a behemoth that has pushed the limits of stellar physics. These eruptions, sudden brightening events accompanied by vast outflows of gas, are not just surface-level explosions. They're signals from the interior of a star fighting a losing battle to maintain equilibrium. But what exactly triggers these eruptions? Why do they happen, and why do they happen in such powerful, unpredictable bursts? The answers lie in a complex interplay of forces, instabilities in the outer layers, opacity fluctuations, and the relentless influence of radiation pressure. At the heart of the matter is the concept of hydrostatic equilibrium, the balance between gravity pulling inward and internal pressure pushing outward. For most of a star's life, this equilibrium is stable. Gravity compresses the core, and the energy from nuclear fusion pushes back, holding the star in a steady state. But in massive stars like P Cygni, which are often over 30 times the mass of our Sun, this balance becomes increasingly fragile as the star evolves. The more massive the star, the higher the pressure and temperature in its core, and the more extreme the forces at play. As P Cygni burns through its hydrogen and begins fusing heavier elements, the fusion zones become more layered and chaotic. Convective turbulence in the outer layers starts to rise, and small disturbances can grow rapidly. This can lead to envelope inflation, where the outer shell of the star swells in size. When this happens, the layers near the surface become less tightly bound by gravity. They're vulnerable, lightly held, easily disturbed, And this is where one of the primary suspects comes into play: radiation pressure. Unlike pressure from gas or heat alone, radiation pressure is unique to very luminous stars. It's the pressure exerted by photons themselves, the force of pure light pushing outward. In low-mass stars, this pressure is relatively small. But in a star like P Cygni, which emits over 500,000 times the luminosity of the Sun, radiation pressure becomes overwhelming. It can exceed the gravitational pull holding the outer layers together. When that happens, a runaway process can begin. The outer layers lift, become unstable, and begin to accelerate outward. The result is an eruption, sometimes so massive that it expels the equivalent of multiple Earths' worth of material into space. But it's not just about the pressure, it's also about how that pressure is absorbed and distributed. That's where opacity comes in. Opacity refers to how easily photons can move through the material inside the star. In regions of high opacity, light gets trapped, building up pressure. In regions of low opacity, light flows freely, and pressure is lower. But in a massive star like P Cygni, opacity is not constant. It changes with temperature, density, and chemical composition. In particular, there are opacity bumps, temperature ranges where the star's material suddenly becomes much more opaque due to the ionization of certain elements, like iron. When one of these opacity bumps is encountered in the stellar envelope, it can trap radiation temporarily. That trapped radiation causes a buildup of internal energy, heating the surrounding gas and expanding the local volume. This expansion reduces density and increases instability, pushing the star toward a tipping point. Once that trapped energy is finally released, it drives a shockwave through the outer envelope, leading to a dramatic outflow. The eruption isn't just a puff of gas, it's the star momentarily losing its ability to hold itself together, like a dam giving way after too much pressure. There's also growing evidence that strange modes of pulsation, non-radial oscillations in the star's surface layers, might be involved. Unlike the predictable, rhythmic pulsations of Cepheid variables, these pulsations are chaotic, multidimensional, and driven by both thermal and dynamic instabilities. They could cause localized expansions or contractions in the outer envelope, which might cascade into full-scale eruptions if they align with periods of opacity-driven radiation trapping. Another layer of complexity is metallicity, the abundance of elements heavier than helium in the star. Stars with higher metallicity tend to have more opaque outer layers, which exacerbates the effects of radiation pressure and increases the likelihood of instability. P Cygni, being located within our galaxy, likely has a moderate to high metallicity compared to more ancient, metal-poor stars. This means that its outer layers are particularly susceptible to the processes that lead to outbursts. The metals present can enhance opacity and contribute to radiation-driven winds that are stronger and more chaotic than in low-metallicity counterparts. It's also possible that the star's rotation plays a role. Though P Cygni is not currently thought to be spinning rapidly, even modest rotation can lead to differential forces across the star's surface. This can create equatorial bulges or polar compression, introducing asymmetries that destabilize the envelope further. If the star had a companion, or even just a history of mass exchange from a past companion, it could have introduced enough angular momentum to influence the outer dynamics. While no companion has yet been definitively detected, the possibility remains intriguing. Some researchers also speculate that magnetic fields could act as a hidden engine behind some of the instability. In some massive stars, strong magnetic loops and field lines trap and redirect stellar material, occasionally channeling it into jets or localized mass ejections. While the magnetic field of P Cygni hasn't been mapped in detail, the irregularity and episodic nature of its eruptions raise the possibility of magnetic involvement, especially if twisted fields snap and release their energy in sudden bursts. Ultimately, what we observe as a luminous outburst from P Cygni is likely the culmination of multiple interwoven processes, a chain reaction that begins with an internal imbalance and ends with a stellar convulsion. It's not one single cause, but a network of triggers and amplifiers. Opacity builds up and traps radiation. Radiation pushes outward and destabilizes the envelope. Pulsations distort the surface. Rotational or magnetic asymmetries worsen the instability. And then, With enough pressure, the surface ruptures and the star coughs out another shell of gas, glowing briefly brighter before settling again into uneasy equilibrium. These are not isolated events. They are part of a long, dying breath, spaced across decades and centuries. And each eruption not only sheds mass, it alters the structure of the star itself, changing its evolution, reducing its final mass, and potentially influencing what kind of supernova it will eventually become. Every outburst is a chapter in that story, a release of pressure, an adjustment to instability, and a warning that this star is nearing the end of its strength. And so, P Cygni doesn't erupt because of one single flaw. It erupts because its entire being is unstable. Its mass, its light, its temperature, its structure, everything about it teeters on a knife's edge. And it has teetered there, impossibly balanced, for centuries. When we talk about P Cygni, we're not just talking about light. We're talking about motion, violent, relentless, unstoppable motion. This star is not merely glowing in the dark, it is exhaling a continuous hurricane of gas and energy. P Cygni's stellar winds are among the most intense and persistent in our galaxy, carrying away its outer layers at hundreds of kilometers per second. These winds are not just side effects of the star's instability, they are central to its identity. They shape its evolution, define its spectral signature, and slowly unmake the star from the outside in. In most stars, including our Sun, stellar winds are gentle. The Sun loses mass at a modest rate, around 1/10 of its total mass per year. But P Cygni operates on an entirely different scale. Its mass loss rate is estimated to be around 10 solar masses per year. That might not sound like much at first glance, but over 1,000 years, that's a full solar mass ejected into space, the equivalent of the entire Sun blown away over just a cosmic blink. In other words, P Cygni sheds in a millennium what it took our Sun billions of years to burn through. And it does so through winds alone. These winds are not chaotic, unfocused outbursts. They are structured and powerful outflows, constantly peeling away the star's outer layers. With speeds reaching 185 to 250 kilometers per second, they hurl vast amounts of hydrogen, helium, and heavier elements into interstellar space. For context, that's fast enough to circle the Earth in about 2.5 minutes. These particles are ejected not in brief episodes, but in a steady, unyielding gale, one that never sleeps. The driving force behind this immense wind is radiation pressure. P Cygni, with its intense luminosity, over 500,000 times the brightness of the Sun, generates a staggering number of photons per second. These photons slam into the atoms and ions in the star's outer atmosphere, especially those of heavier elements like iron and nitrogen. When a photon is absorbed by an atom, it imparts momentum, pushing the atom outward. With enough photons, and enough momentum transfers, a massive wave of material is driven away from the star's surface. This is the mechanism of line-driven winds, and in P Cygni, it operates with extraordinary efficiency. In fact, the very phenomenon that gives the star its unique spectral P Cygni profile, a combination of emission lines and blue-shifted absorption, is a direct result of these winds. The absorption features occur as photons from the star's core pass through the outward-moving gas, while the emission features come from the ionized material glowing in the extended envelope. That profile is not just a diagnostic tool, it's a signature, a daily reminder that P Cygni is bleeding its mass into space. But this isn't just a matter of erosion. These winds have cosmic consequences. As the wind carries mass into the surrounding space, it enriches the interstellar medium with elements forged in the star's interior. Over time, the hydrogen and helium expelled by P Cygni mix with carbon, nitrogen, and oxygen, key ingredients for forming new stars, planets, and potentially life. Every gram of mass lost is not lost to oblivion, it becomes part of the galaxy's future. Moreover, these winds interact with previously ejected material, forming shock fronts, shells, and bubbles of hot gas. When older, slower-moving gas is overtaken by new, faster-moving winds, collisions occur, heating the gas to millions of degrees and creating X-ray emission regions. These interactions can be studied through infrared and radio imaging, revealing the full scale and structure of P Cygni's past and present activity. In fact, astronomers have detected multiple expanding shells around the star, relics of both ancient eruptions and continuous winds, all radiating outward like the rings of a cosmic tree trunk. This expanding atmosphere has another consequence: it alters the star's apparent size. While P Cygni's core radius is around 75 times that of the Sun, the dense wind creates an extended, diffuse envelope that can stretch much farther into space. To observers using interferometry or other high-resolution imaging techniques, the star appears larger than its actual core, surrounded by a fuzzy halo of flowing gas. And as the star continues to lose mass, the balance of forces within it shifts. Mass loss reduces gravitational pressure, changing the fusion dynamics in the core. It also strips away the hydrogen-rich outer layers, potentially exposing deeper layers of helium or even heavier fusion products. Over time, this process could lead P Cygni into the Wolf-Rayet phase, a late evolutionary stage characterized by even more extreme winds, even greater mass loss, and a much higher surface temperature. Wolf-Rayet stars are ticking time bombs, only a step or two away from collapse. If P Cygni does evolve into this phase, its winds will intensify further, pushing it closer to its final act. Despite this violence, the star remains stable in a strange sort of way. It doesn't tear itself apart in one grand event, but disassembles itself gradually, shell by shell, stream by stream. The winds are relentless but controlled, like a furnace venting pressure to prevent a total breakdown. And this long, sustained wind phase gives astronomers a unique opportunity to study the death of a massive star in real time, over decades and centuries, rather than in a fleeting moment. The challenge for modern science is to model these winds accurately. They're not uniform. They're clumpy, structured, and time variable. They may contain arcs, filaments, or asymmetric flows. Simulations must take into account not just radiation pressure, but magnetic fields, rotation, metallicity, and turbulence. Every factor affects how mass is lost, and how quickly. And that, in turn, influences whether P Cygni will collapse into a black hole, explode in a hypernova, or perhaps transition into an even rarer end state. In short, the winds of P Cygni are not just a symptom of dying, they are the method of death itself. Every atom blown away is a part of the star's being, cast into the galaxy to wander in darkness. And as the star's body thins, its core draws ever nearer to its final fate. But it doesn't go quietly. It goes like a storm. P Cygni is not a gentle star. It's not modest in size or shy in temperament. It is a giant, a true heavyweight in the stellar hierarchy, one of those rare cosmic entities born with more mass than it can safely handle. At the peak of its main sequence life, P Cygni is estimated to have had a mass of roughly 30 times that of the Sun, although this figure, like many in stellar astrophysics, is wrapped in uncertainty due to the immense complexity of such stars. Over time, its intense stellar winds and eruptions have whittled that figure down, perhaps to something closer to 25 or even 20 solar masses today. Still, even on the low end, this mass places P Cygni in the top tier of stellar giants. And mass, in the universe, is destiny. To appreciate how mass governs P Cygni's life, we must return to the core principle that defines all stars. The more mass a star has, the faster it lives and the sooner it dies. Mass dictates the amount of pressure in the core, which in turn determines the star's internal temperature and rate of nuclear fusion. A low-mass star like our Sun burns its hydrogen calmly over billions of years. But a star with 30 solar masses burns like a blowtorch. It fuses hydrogen at a vastly accelerated rate, consuming its nuclear fuel in a fraction of the time. P Cygni's main sequence lifespan, in which it fused hydrogen into helium in a stable core, likely lasted only about 5 to 7 million years, a mere blink in the cosmic timeline. Once that central hydrogen supply was exhausted, the star began its descent into instability. The core shrank and heated up, and the outer layers expanded, pushing P Cygni off the main sequence and into the luminous blue variable phase. Here, its enormous mass played an even more dramatic role. The gravitational pressure in the core reached such heights that fusion of heavier elements, helium, carbon, oxygen, became possible. But with each new fuel, the process becomes increasingly dangerous and short-lived. Fusion of helium lasts just a few 100,000 years. Carbon burns for thousands. Oxygen and silicon burn for mere days in the final moments of the star's life. This burning staircase leads to one endpoint: iron, the dead end of fusion. Iron cannot be fused to release energy. Instead, it consumes energy. When P Cygni eventually builds up a core of iron, if it survives long enough, no outward pressure will be able to stop gravity from winning. The core will collapse in milliseconds, triggering a supernova or possibly something even more energetic. But mass doesn't just dictate how the core evolves, it also determines how unstable the outer layers become. P Cygni is constantly balancing its enormous internal luminosity, 500,000 suns worth of radiant energy, against the gravitational pull of its bulk. This creates an inherently fragile equilibrium, where even slight perturbations can lead to dramatic eruptions. The more mass P Cygni started with, the more powerful its radiation pressure became, and the more violently it could throw off its own outer layers. In fact, the threshold for luminous blue variable behavior appears to begin around 20 solar masses, meaning P Cygni's original 30+ solar masses made it almost destined to become such a star. Interestingly, the loss of mass over time changes P Cygni's fate in real time. The more mass it sheds, the less tightly gravity can bind its atmosphere. But paradoxically, if it loses too much mass before reaching core collapse, it might avoid a traditional supernova altogether. Instead, it could collapse quietly into a black hole, without the fireworks. This mass threshold, between roughly 20 and 40 solar masses, marks a kind of cosmic tightrope. Fall below it, and you may become a neutron star. Stay above it, and your death will be shrouded behind an event horizon. But there's more. P Cygni's mass also affects the chemical enrichment of the galaxy. Massive stars like this act as cosmic alchemists, fusing lighter elements into heavier ones and then dispersing them through winds and explosions. Every ton of gas flung into space carries with it the seeds of future stars, planets, and possibly life. Without high-mass stars like P Cygni, the universe would lack the carbon in your cells, the oxygen in your lungs, and the calcium in your bones. Stars of this size don't just die spectacularly, they build the universe as they go. Another consequence of P Cygni's mass is its sheer luminosity and size. With its immense core pressure, the star's radius ballooned to around 75 times that of the Sun, and possibly even larger if you include the extended atmosphere caused by its stellar winds. This bloated size means that the energy from the core has to travel farther through increasingly unstable outer layers, which are prone to convection, turbulence, and eruptions. The vastness of the star itself creates more surface area for instability and more opportunities for mass to be lost to space. It's also worth noting that this mass comes with complications for astronomers. Measuring it precisely is extraordinarily difficult, especially without a binary companion to provide gravitational data. Most estimates rely on spectral modeling, wind velocity, and luminosity comparisons with stellar evolution tracks. This adds uncertainty, but even the most conservative models agree P Cygni began its life with enough mass to end it in dramatic fashion. Finally, as we look ahead, we understand that P Cygni's mass is the clock counting down toward its destruction. It's the reason the star has lived fast, burned bright, and aged violently. Each kilogram it loses reshapes its future, narrows its possible end states, and influences the shockwaves it will send through the cosmos. P Cygni is massive enough to become a black hole, massive enough to light up the sky in a supernova, and massive enough to rewrite its surroundings with every outburst. In the end, P Cygni is not just another point of light in the sky, it's a stellar juggernaut, a relic of extreme physics, and a messenger from the era of cosmic giants. It was born to blaze, and it will die with the same unstoppable force that made it a legend. P Cygni doesn't just whisper its past through light curves or spectra, it shouts it into space, carving its own history into the fabric of the cosmos. Like the rings in a tree trunk or the ripples from a stone tossed into a pond, the space around this star bears the fingerprints of its long, violent life. Surrounding P Cygni are vast, expanding shells of gas, remnants of outbursts that happened not just decades but centuries ago. These shells are the fossilized echoes of its eruptions, and astronomers have learned to read them like celestial archaeology. These gas shells didn't remain hidden forever. For centuries, observers tracked the changes in P Cygni's brightness, puzzled by its variability but unaware of the full extent of what it was leaving behind. Then, as infrared astronomy advanced and imaging technology improved in the late 20th and early 21st centuries, astronomers began to peer deeper into the murky regions surrounding the star. What they found confirmed a long-suspected theory: P Cygni had not only experienced episodic brightening, it had violently expelled physical material into space, and this material was still out there, expanding away from the star in vast arcs and spheres. The most prominent of these is a nearly spherical nebula, faint but detectable, extending outward in all directions from the star. This structure is made of ionized gas, primarily hydrogen and nitrogen, that had been expelled during one of P Cygni's great outbursts, likely the 1600 AD eruption or a similar event from that era. It expands at a measurable velocity of approximately 140 km per second, and using that speed along with the current size of the nebula, astronomers can trace its origin back in time. The age calculations of the nebula line up almost perfectly with the timeline of the 1600 outburst, providing a stunning confirmation that what was seen by skywatchers centuries ago left a permanent, physical imprint on the interstellar medium. But it doesn't end with just one shell. Infrared observations, especially from space telescopes like Spitzer and Herschel, have revealed multiple concentric structures, as if P Cygni has been pulsing outward repeatedly over long timescales. These layers may correspond to a series of eruptions or sustained periods of increased mass loss, each separated by decades or centuries. Unlike the fast, sharp bursts of novae, these shells seem to form in slower, denser episodes, more akin to a volcanic eruption than a supernova. They cool as they expand, eventually reaching temperatures where they begin to emit in infrared and even sub-millimeter wavelengths. This is where modern observatories have been most successful in imaging them. The shells themselves are not uniform. They are clumpy, fragmented, and shaped by the winds that followed them. After a major outburst, P Cygni's stellar wind continues, blowing through the gas it just expelled. This wind collides with the inner edge of the shell, compressing and heating it, creating shock fronts and complex filamentary structures. These interactions leave behind intricate patterns, bright knots of ionized gas, arcs of dust, and turbulent edges that shimmer with the energy of their collision. The shells are not just passive remnants. They're dynamic, evolving structures, still reacting to the forces that expelled them centuries ago. This detection of multiple shells also reinforces the idea that P Cygni is not a one-time outburster, but a recurrent monster, a star that has undergone several violent episodes over the course of its post-main sequence life. Each shell records the story of one of those moments. And the further out a shell lies, the older the event it represents. By studying the velocity and composition of each shell, astronomers can reconstruct a timeline of instability, a kind of stellar biography written in gas and dust. Spectroscopy of these shells reveals more than just age. It tells us about the chemical makeup of the material ejected. Enriched in elements like nitrogen, these shells bear the signs of internal fusion processes. The ejected gas isn't just leftover hydrogen, it's processed material, formed during the fusion of hydrogen into helium and beyond. This gives us insight into what's happening deep within the star, even though we can only observe the outer envelope directly. In essence, these shells are samples from the star's fusion core, flung into space by forces too powerful to contain. In some cases, light echoes from these ancient eruptions can also be detected. These are reflections of past flashes of light, bouncing off distant dust clouds and arriving at Earth centuries after the event. Light echoes allow astronomers to observe the same eruption from multiple angles, and even to effectively look back in time. While no confirmed light echoes from P Cygni's 1600 eruption have been captured yet, it remains an active area of interest. The complex interplay of expanding gas and surrounding interstellar dust means it's possible, perhaps even likely, that some echoes are out there, waiting to be discovered by future telescopes with even more sensitive instruments. Another valuable aspect of these shells is that they help to distinguish luminous blue variables from other types of variable stars. not all variable stars expel material. Not all stars leave behind shells that persist for centuries. But in LBVs like P Cygni and Eta Carini, the presence of nebulae and expanding gas is a defining trait. These shells are not just decorations, they are evidence of an internal instability that is not yet fully understood. They show us that the variability we see in light curves is not just a surface phenomenon, it's a symptom of explosive mass loss and internal chaos on a truly massive scale. These structures also play a role in modeling P Cygni's future. By estimating the rate at which it's losing mass, and by comparing the time intervals between shell formation, scientists can project how long the star has before reaching critical mass thresholds that would trigger core collapse. Every shell narrows the window. Every new outflow changes the internal equilibrium. Eventually, one of these pulses may be the last. To an observer, P Cygni appears almost serene now, a bright star in the constellation Cygnus, shining steadily in the night. But space tells a different story. If we could see in the right wavelengths, we'd witness a history of upheaval all around it, layers of expanding gas, like ghostly exhalations, tracing every moment the star couldn't hold itself together. The shells don't just surround P Cygni. They define it. They are its memory made visible. They are what remains when light fades but matter still speaks. When a star like P Cygni erupts, the brilliance of its outburst radiates outward in all directions, a sudden blaze of light illuminating the cosmos. But unlike the physical shells of gas that march steadily away from the star, this light travels much faster, at the speed of light itself, racing across the interstellar medium. And sometimes, it doesn't travel in a straight line to Earth. Sometimes it bounces, reflects, deters. And in doing so, it creates one of the most remarkable phenomena in astrophysics, the light echo. A light echo is, in essence, a delayed replay of a stellar event. When a luminous burst of light from a star strikes surrounding clouds of interstellar dust, some of that light is scattered and redirected toward Earth. Because it travels a longer path, bouncing off the dust rather than traveling directly, we receive it after the original light has already passed. This means that centuries after a stellar outburst, we might still detect echoes of it rippling through space. It's as if the universe itself preserves the moment in a vast three-dimensional theater, with light bouncing off the walls long after the show has ended. For a star like P Cygni, which experienced a dramatic brightening in the year 1600 AD, this concept is more than theoretical. If surrounding dust clouds are positioned just right, at the correct angles and distances, then it's possible that reflected light from that ancient eruption is still traveling toward us today, centuries after the event occurred. That light would carry with it the spectral fingerprint of the eruption, allowing astronomers to study the explosion not through old records or speculation, but as if it were happening now. This is not science fiction. It's science fact. Light echoes have been observed around other eruptive and explosive stellar phenomena, most famously, in the aftermath of SN 1987A, a supernova in the Large Magellanic Cloud. In that case, astronomers not only captured the explosion as it happened but also saw concentric rings of light expanding outward through dust clouds, visible proof of the light echo process. Later, these echoes allowed scientists to measure the geometry of the surrounding space, to track the expansion speed of the supernova remnant, and even to reanalyze the explosion's spectrum years after the fact. The same potential exists for P Cygni. If light from its 1600 outburst bounced off a cloud of dust located, say, a few hundred light-years behind the Earth relative to the star, that light could still be en route to us, arriving with the same information it carried centuries ago. And if detected, this light would allow astronomers to reconstruct the eruption in exquisite detail, its temperature, composition, velocity, and energy output. It would be like finding a buried photograph of a long-lost moment in time, perfectly preserved. Searching for such echoes is not simple. It requires infrared and optical surveys with high sensitivity and wide coverage, as well as careful modeling of the geometry of the surrounding interstellar medium. Instruments like those aboard the Hubble Space Telescope, the Spitzer Space Telescope, and now the James Webb Space Telescope, JWST, are uniquely suited to this challenge. These telescopes can resolve faint reflections against the clutter of the Milky Way and detect subtle changes in the structure of dust clouds over time. Moreover, ground-based observatories with long-term monitoring capabilities, such as those used in time-domain astronomy, can search for transient brightening in surrounding dust regions near P Cygni. If a patch of space suddenly becomes slightly brighter without an obvious source, it may be an echo, a time capsule of light that's just now completing its journey. What makes light echoes so extraordinary isn't just their beauty or rarity. It's the information they carry. Light doesn't just illuminate, it encodes. Within a single reflected beam are the fingerprints of the stellar surface, the velocities of ejected material, the temperature of the eruption, and even changes in chemical composition. A light echo from P Cygni's great outburst would not only confirm historical accounts of its brightness increase, it would tell us what that explosion actually was. Whether it was a true giant eruption akin to Eta Carini's 1843 event, a brief Super Eddington episode, or a hybrid of both. Even more intriguingly, light echoes can sometimes reveal things that were missed in real time. Subtle changes in the outburst, asymmetries in the expansion, or previously hidden phases of cooling can all become visible when viewed from different angles via reflections. It's like watching the same event from a different seat in the stadium, and discovering new details every time. Light echoes also serve a larger purpose. They are part of the new frontier in time-domain astronomy, where we no longer just observe the present, but actively recover the past. In this way, the cosmos becomes a memory bank, recording flashes of violence and beauty in the very dust that drifts between the stars. For P Cygni, the search for echoes is a search for truth across time, a chance to piece together the events that shaped its evolution and to understand its place in the broader narrative of massive star death. The echoes of P Cygni may still be on their way to us, quietly weaving through space at 300,000 kilometers per second. When they arrive, if they arrive, they will not come with a bang, but with a whisper, a faint shimmer, a subtle flare. And in that whisper will lie a story 400 years old, as fresh as the day it was born. P Cygni, with all its brilliance and unpredictability, is far from alone in the celestial menagerie of stellar giants. It belongs to a rare and tempestuous family of stars known as luminous blue variables, LBVs, a class marked by volatility, grandeur, and often, destruction. But even within this exclusive class, each LBV tells its own violent, unstable story. To understand P Cygni more deeply, it helps to hold it up against its stellar siblings, particularly Eta Carini and Ag Carini, two of the most intensely studied LBVs in the sky. By comparing their behaviors, structures, and life trajectories, we uncover not only the diversity within this class of stars but also the defining traits that bind them together. Let's begin with Eta Carini, a true titan among stars. Located roughly 7,500 light-years from Earth in the Carina constellation, Eta Carini is one of the most massive and luminous stars known, boasting an original mass of perhaps 100 to 150 times that of the Sun, and a luminosity exceeding 5 million suns. It's a giant among giants, outshining P Cygni by an order of magnitude in sheer energy output. Yet, like P Cygni, Eta Carini is dangerously unstable, teetering on the brink of self-destruction for centuries. Eta Carini's most famous episode, its great eruption of the 1840s, dwarfed P Cygni's 1600 event in scale. During that explosion, Eta Carini brightened to become the second brightest star in the sky, and for a brief time, it rivaled Sirius in luminosity. It expelled at least 10 to 20 solar masses of material into space, an eruption so intense that it created the now iconic Homunculus Nebula, a bipolar cloud of glowing gas that continues to expand outward to this day. Compared to Eta Carini's eruption, P Cygni's historical outbursts were modest, releasing far less mass and never achieving such extreme brightness. But while Eta Carini is the more powerful and dramatic of the two, it is also more enigmatic. It is likely a binary system, and the presence of a massive companion star plays a major role in its behavior, triggering periodic outbursts and influencing the shape of its nebula. P Cygni, by contrast, is not known to be in a binary system, or if it is, its companion is undetected and subtle in its effects. This difference makes P Cygni a more straightforward case for studying intrinsic LBV variability, a kind of baseline example of how a single, unstable star behaves without external gravitational disturbances. In that sense, P Cygni is the control subject in the chaotic laboratory of LBVs, while Eta Carinii is the wild experiment. AG Carinii provides another important point of comparison. This LBV, also located in the Carina constellation, shares many similarities with P Cygni, albeit with a slightly higher mass, estimated around 50 to 70 solar masses. Like P Cygni, AG Carinii has experienced repeated episodes of brightening and dimming, as well as intense stellar wind-driven mass loss. But what makes AG Carinii fascinating is its prolonged periods of quiescence punctuated by sudden outbursts. During these phases, the star can change its spectral type, temperature, and apparent size drastically, as it expands and cools, or contracts and heats in a matter of months or years. Where P Cygni has remained relatively stable since its great outburst in the 1600s, never again achieving such dramatic changes in brightness, AG Carinii continues to fluctuate dramatically. This makes AG Car a kind of intermediate between the extremes of P Cygni's relative dormancy and Eta Carinii's cataclysmic violence. AG Car's variability is especially valuable for studying the internal mechanisms that drive LBVs to switch between hot and cool phases, and how those cycles influence mass loss and evolution. P Cygni, on the other hand, appears to be stuck in a kind of long-term post-outburst recovery, with lower-level activity that nonetheless reveals the signature winds and spectral characteristics of the LBV phase. There's also the matter of nebular structure. All three stars, P Cygni, Eta Carinii, and AG Carinii, are surrounded by expanding shells of gas, material expelled during past eruptions. But these nebulae differ in structure and scale. P Cygni's nebula is more spherical and diffuse, lacking the dramatic bipolar outflows of Eta Carinii's homunculus. AG Carinii's nebula, meanwhile, exhibits a more chaotic, filamentary pattern, suggesting multiple asymmetric outbursts or complex wind interactions. These differences tell us that while the physics of LBVs are governed by common principles, mass, radiation pressure, stellar winds, the exact morphology of their ejecta can vary wildly, likely influenced by magnetic fields, rotation rates, and local environments. Temperature is another point of comparison. During quiescent phases, P Cygni maintains a surface temperature of around 18,000 to 20,000 K, while AG Carinii and Eta Carinii fluctuate much more dramatically. Eta Carinii has a lower visible surface temperature due to dense winds that obscure the hotter inner layers, while AG Carinii can drop to 8,000 K in its cool phase, resembling a yellow supergiant, and then heat back up to 25,000 to 30,000 K when it returns to a hotter state. P Cygni doesn't undergo such wild swings, which again underscores its relative stability among a group of unstable stars. Then there is the ultimate question: which of them will go supernova first, and how? Eta Carinii, with its enormous mass and violent history, is the prime suspect for apparent stability supernova or direct collapse into a black hole, possibly without a traditional explosion at all. AG Carinii, with slightly lower mass, might still produce a spectacular core collapse event, depending on how much mass it loses beforehand. P Cygni, now much lighter than either of them due to sustained mass loss, might be on track for a Type II supernova, unless it loses so much mass that it transitions into a Wolf-Rayet star and dies as a stripped envelope supernova like Type IB or IC. Each LBV is a variation on a theme, a massive star in crisis, shedding its skin to delay the inevitable. But the tone and tempo of that crisis vary dramatically. P Cygni is a slow, simmering fire, bright, dangerous, but steady. Eta Carinii is a powder keg that already exploded once and may do so again. AG Carinii is the restless one, flickering between extremes as if uncertain which path to take. Together, they give astronomers a composite picture of LBV behavior, the timing, triggers, and trajectories of some of the most volatile stars in the universe. And among them, P Cygni stands as the quiet chronicler, less violent, perhaps, but no less important. It teaches us that not all eruptions need to be spectacular to be significant, and that the stars that burn brightest are not always the loudest. In the vast and complex world of stellar physics, there's one subtle but crucial ingredient that often hides behind the scenes, quietly shaping a star's fate: metallicity. In astronomy, metals refer to all elements heavier than hydrogen and helium, oxygen, carbon, nitrogen, iron, and more. These elements might make up only a small fraction of a star's mass, but their influence on that star's winds, stability, brightness, and evolution is profound. And for a luminous blue variable like P Cygni, metallicity is one of the hidden levers behind its immense power and its eventual demise. At first glance, the idea that a star's metal content could influence its behavior might seem counterintuitive. After all, hydrogen is the main fuel of stars, and helium is the product of that fusion. Why should the trace presence of elements like iron or nitrogen matter so much? The answer lies in how radiation interacts with matter. P Cygni, like all massive stars, radiates a staggering amount of energy. Its luminosity is over 500,000 times that of the Sun, which means it pours out photons at a furious rate. These photons interact with the star's outer layers, particularly with the atoms in its extended atmosphere. When the outer layers contain more metals, especially ions like Fe2, iron, CNO elements, carbon, nitrogen, oxygen, those atoms absorb photons more efficiently. This leads directly to line-driven winds, a process in which radiation pressure, acting on specific absorption lines in a star's spectrum, transfers momentum to the gas and pushes it outward. The more metal ions there are to absorb photons, the more effective this mechanism becomes. In essence, metals act as photon sails, catching the radiation and using its energy to drive mass out into space. P Cygni's high metallicity is one of the reasons its winds are so powerful, ejecting mass at rates of up to 10 solar masses per year. That's about 1,000,000 times more than what our Sun loses annually. And this metal-driven wind doesn't just affect how much mass the star loses, it influences how stable or unstable the star becomes. The more efficient the wind, the more material the star can shed, which can reduce its mass, alter its internal equilibrium, and push it into different phases of its life cycle. In fact, it's no coincidence that LBVs like P Cygni tend to form in regions of the galaxy with relatively high metallicity, such as the Milky Way's inner regions or in other metal-rich spiral galaxies. In contrast, when we observe massive stars in metal-poor environments, like the Small Magellanic Cloud, SMC, we find far fewer LBVs. These stars still shine brightly, but without the same metal content, their winds are weaker, their mass loss slower, and their paths through stellar evolution more gradual and less dramatic. This difference matters because it suggests that metallicity helps determine not just how a massive star dies, but when and how violently. For stars like P Cygni, rich in heavy elements, the enhanced wind accelerates mass loss, strips away the hydrogen envelope earlier, and potentially causes the star to transition into a Wolf-Rayet star phase sooner. This makes a supernova or black hole collapse more likely in a shorter time frame. For low metallicity stars, the winds may not be strong enough to initiate these transitions before core collapse, which could result in different types of supernovae, or even silent collapses. Moreover, metallicity also affects the opacity of the stellar atmosphere, the measure of how transparent or opaque the outer layers are to escaping radiation. A more opaque atmosphere, thanks to metals absorbing photons, traps heat and radiation, making the outer layers less stable. In LBVs like P Cygni, this contributes to the irregular and violent behavior we associate with the class: sudden eruptions, brightness variations, and shell ejections. When the opacity gets too high, the radiation pressure can exceed gravitational pull in localized regions of the star's envelope. This creates turbulent instabilities that can lead to massive surface eruptions, like the ones P Cygni experienced in the early 1600s. Without high metallicity, those instabilities might never grow large enough to trigger such events. Another interesting consequence of metallicity is its impact on observability. Because metals are responsible for many of the lines in a star's spectrum, high metallicity stars like P Cygni produce a much richer and more detailed spectral signature. This allows astronomers to identify features like the famous P Cygni profile, a combination of emission and blue-shifted absorption lines caused by its winds. These spectral fingerprints are invaluable for studying the star's wind velocity, mass loss rate, and chemical composition in real time. But the story doesn't end there. Metallicity is also a record of ancestry. The heavy elements in P Cygni were not created in isolation. They were forged in the cores of earlier generations of stars and scattered into space by long-dead supernovae. P Cygni is a second or third generation star, born in a region of space already enriched by the cosmic recycling of elements. Its violent winds and eventual death will, in turn, seed future generations of stars with even more heavy elements. In this way, metallicity is not just a driver of stellar behavior, it's part of a galactic evolutionary loop, where one star's end becomes the next star's beginning. As we study stars like P Cygni across different regions of the galaxy and beyond, we find that metallicity is a key variable in modeling the fates of massive stars. It helps explain why some stars explode as Type II supernovae while others become black holes in silence. It explains why some stars lose their outer layers in a graceful wind, while others burst apart in furious eruptions. And it shows us that the tiniest fraction of a star's makeup, those precious 1 to 2% of metals, can dictate the outcome of a million solar luminosity life. In P Cygni's case, its high metallicity is both a gift and a curse. It grants the star a voice loud enough to roar across the cosmos through its winds, but it also sets the clock ticking faster toward collapse. The very elements that allow it to shine and erupt are the ones that guarantee its downfall. For a star that once burst forth with such violent drama, P Cygni's long-term calm is one of the great paradoxes of stellar astrophysics. After its great outburst in the early 1600s, an event so intense it briefly made the star visible to the naked eye, it would be natural to expect a repeat performance. And yet, centuries have passed, and the star has remained eerily stable, at least in terms of visible brightness. For a member of the tempestuous luminous blue variable, LBV class, this behavior seems almost out of character. So what's going on? Why has P Cygni, once a poster child for stellar instability, settled into such a long-lived period of quiet, when other LBVs like Eta Carini and AG Carini continue to fluctuate or erupt? The answer isn't simple, and astronomers have proposed several interconnected explanations that attempt to decode this apparent contradiction. To begin with, it's important to define what stability really means in the context of a star like P Cygni. While it hasn't had any massive, explosive eruptions in recent centuries, it still exhibits subtle fluctuations in its spectrum, wind velocity, and mass loss rates. These changes are real and measurable. They just don't manifest in dramatic increases in visual brightness like the eruption of 1600. So the stability we observe is mostly photometric, that is, stability in light output as seen from Earth. One leading hypothesis suggests that P Cygni may now be in a post-eruption recovery phase. After the great outburst of the 1600s, the star could have shed a substantial portion of its outer envelope, enough to temporarily relieve the internal pressure and radiation buildup that triggered the eruption in the first place. In this view, the eruption acted as a kind of release valve, venting off the accumulated instability and restoring temporary equilibrium. If so, what we're seeing now is not so much true stability as the quiet aftermath of a massive internal restructuring. This idea is supported by the presence of expanding gas shells around the star, which bear the fingerprint of past mass loss events. These shells show that P Cygni has already gone through several violent episodes, likely spaced over thousands of years. The eruption seen in 1600 may have been the most recent in a long, episodic cycle. If this cycle continues, P Cygni might remain visually steady for hundreds, or even thousands more years before the next eruption, making our era just a particularly calm chapter in its otherwise turbulent biography. Another factor contributing to P Cygni's visual consistency is the nature of its current mass loss mechanism. Instead of eruptive events, the star is now primarily shedding mass through steady, high-velocity stellar winds, an ongoing but relatively gentle process compared to explosive outbursts. These winds carry away matter at a significant rate, but do so gradually, keeping the outer layers from accumulating the kind of instability that would lead to another bright eruption. This quasi-steady wind phase could be acting as a pressure release system, maintaining balance between the internal energy generation and the gravitational hold of the star's envelope. It's also worth considering the opacity modulation hypothesis, which involves changes in the way radiation is transported through the star's outer layers. LBVs are highly sensitive to small changes in their internal structure, particularly in regions where iron opacity peaks, layers where certain ionized metal atoms suddenly become more opaque to radiation. This can create temporary pressure buildups and drive expansions or contractions of the star's photosphere. If P Cygni has reached a point where these opacity fluctuations are being moderated, either by previous mass loss or by reaching a more stable temperature-pressure gradient, then it might have entered a phase of thermal equilibrium, suppressing the kind of envelope disruptions that cause visual brightening. And then there's the role of rotational velocity and magnetic fields. While neither has been definitively measured in P Cygni to the precision needed for a full model, it's possible that internal angular momentum redistribution or magnetic field stabilization after past eruptions has helped the star enter a more stable phase. In stars of this mass and luminosity, even small differences in rotational rate can have large effects on mixing, wind behavior, and surface instability. If P Cygni is rotating relatively slowly, it may be experiencing reduced mixing of heavier elements into its envelope, which in turn dampens the cycle of internal feedback that often leads to instability in more rapidly rotating LBVs. Finally, we must acknowledge a sobering truth: our observational window is very narrow. P Cygni has been closely monitored for just a few centuries, a cosmic blink. For a star that might live only a few million years, a few hundred years of quiet could easily be part of a longer, more variable pattern. It's entirely possible that P Cygni's current stability is temporary, and that the star will once again erupt, perhaps tomorrow, perhaps in 1,000 years. LBVs are inherently unpredictable. The very definition of this class is based on erratic behavior. That P Cygni has been quiet for our lifetime doesn't mean it has always been so, or always will be. In fact, some recent spectroscopic analyses suggest that even now, the star's atmosphere is slowly changing. The wind velocity, temperature profile, and line broadening in its spectrum hint at ongoing, subtle shifts beneath the surface. These may be the early warning signs of a new cycle of instability, an indication that the star is once again moving toward a critical threshold. In sum, the mystery of P Cygni's current stability may be less a contradiction and more a reflection of its cyclical nature. It erupted once, and it may erupt again, but in the meantime, it has entered a plateau of quasi-equilibrium, maintained by the very same winds and internal processes that once made it explode. It is stable now, not because it is peaceful, but because it is recovering, resting, gathering, the calm between storms. The question that looms over P Cygni like a silent clock is this: will it end in a supernova? And if so, what kind of cosmic finale awaits this luminous blue variable? A star that has already erupted with such force and spectacle that it reshaped the way we study massive stars. To answer that, we must dive into the intricate and still evolving theories about how the most massive stars die, and how the particular traits of P Cygni, its mass, its structure, its wind-driven past, align with the known pathways to stellar death. First, we must acknowledge the basics. P Cygni is massive, roughly 25 to 30 times the mass of the Sun by current estimates. That alone places it well within the range of stars that are expected to end their lives not quietly, but in a violent explosion. Stars more massive than about 8 solar masses are virtually guaranteed to experience core collapse at the end of their lives, when nuclear fusion can no longer support the weight of the overlying layers and the core collapses in on itself. For a star like P Cygni, that eventuality is almost certain. But how it dies, and what kind of supernova it produces, depends on what happens between now and then. And that, in turn, depends on how much mass it loses. You see, stars like P Cygni are engaged in a race against themselves. On the one hand, gravity is constantly trying to pull the star inward. On the other, fusion in the core pushes outward. When that balance tips, collapse occurs. But if the star loses a significant portion of its mass before reaching that point, its structure, and thus the kind of explosion it produces, can change drastically. The history of P Cygni's mass loss, including the eruption of 1600 and the steady wind-driven shedding that continues today, will shape what kind of supernova it becomes. If P Cygni retains most of its hydrogen envelope, it is likely to end as a Type 2P supernova. This is the classic model. A massive star with a thick hydrogen outer layer explodes, and the resulting light curve shows a plateau phase, where the brightness remains constant for weeks or months as the expanding gas slowly cools and recombines. These are among the most common core collapse supernovae observed. The hydrogen in the outer layers reprocesses the energy from the collapsing core, creating the distinctive plateau. But here's the twist: P Cygni may not keep most of its hydrogen. Over hundreds of thousands of years, it has already lost a sizable fraction of its mass. Its current rate of mass loss, driven by its powerful stellar winds, could strip the star of its outer hydrogen layers entirely by the time it collapses. If that happens, we enter the territory of Type IB, or IC supernovae, collectively known as stripped envelope supernovae. These are explosions where the progenitor star has lost either some, most, or all of its hydrogen, and sometimes even its helium, resulting in a much shorter, sharper light curve and different spectral signatures. A Type IB supernova lacks hydrogen lines but retains helium, while a Type IC lacks both. These types of supernovae are thought to come from stars that were once LBVs or Wolf-Rayet stars, the evolutionary phase that often follows the LBV stage. If P Cygni continues on its current trajectory, shedding mass through strong winds or another eruptive event, it could become a Wolf-Rayet star itself. These stars are extremely hot, luminous, and entirely devoid of hydrogen envelopes, exposing their helium-burning cores. They are the dying breaths of once massive stars, and their explosions are among the most energetic in the universe. Now, in the most extreme theoretical case, if P Cygni manages to maintain a core mass that is both very large and rapidly rotating, it might be a candidate for something even more dramatic, a hypernova. This class of explosion, first proposed to explain the incredible energy seen in certain supernovae, especially those associated with long-duration gamma-ray bursts, involves the formation of a rapidly spinning black hole at the core. The core collapse is accompanied by an accretion disk that funnels energy into powerful relativistic jets, which in turn may punch through the outer layers and emit gamma rays observable across billions of light years. However, this outcome is considered less likely for P Cygni. To become a hypernova progenitor, a star typically needs to retain a great deal of angular momentum, and P Cygni's slow rotation, possibly slowed further by strong mass loss episodes, suggests it may not fit the profile. Hypernovae also seem to occur more often in low metallicity environments, where the winds are weaker and stars lose less angular momentum. P Cygni, being relatively metal-rich, likely experience significant rotational braking over time. There is also the possibility that P Cygni could collapse silently, without a visible supernova at all. If the core collapses and the outer layers fall in quickly enough, the star might collapse directly into a black hole, especially if its final mass exceeds certain thresholds and the explosion energy is insufficient to eject the outer layers. In such a case, the star would simply disappear from the sky, fading like a dying ember without a flash. While chilling, this outcome is theoretically possible for stars in the 20 to 30 solar mass range, particularly those that lose enough mass to avoid a full-blown supernova but not enough to avoid gravitational collapse. Ultimately, the question of whether P Cygni will explode, and how, remains unresolved. What we do know is that it has the mass, luminosity, and evolutionary path required for a violent end. It is almost certainly in its final few 100,000 years, possibly less, and the physical processes now playing out in its core are steadily marching toward collapse. The key uncertainty is how much more mass it will lose before that day comes. If it loses a little, Type 2 supernova. If it loses a lot, Type IB or IC supernova, or even direct collapse. If something unexpected happens, such as a late-stage merger or unusual nuclear burning, who knows? What makes this all the more fascinating is that we may, in some cosmic sense, be watching a countdown. Every spectrum, every wind measurement, every whisper of change in P Cygni's envelope may be another tick of the clock. And if that final tick comes in our lifetime, we would witness one of the most dramatic events the human eye can behold, the death of a massive star in a blaze of cosmic fire. But until then, P Cygni remains a candle burning at both ends, shedding light, shedding mass, and preparing, in silence, for its spectacular end. P Cygni is more than a single point of light in the night sky. It's a living, breathing laboratory, an astronomical time capsule frozen in a rare and fleeting phase of stellar life. In the grand narrative of cosmic evolution, it serves as a precious and irreplaceable window into the fate of the universe's most massive stars. Its every tremble, wind, pulse, and eruption offers insights into questions that continue to challenge astronomers. How do the most massive stars evolve? What causes them to shed their mass so violently? And how do these brief, brilliant lives end? Massive stars are strange creatures. They burn brighter, live faster, and die younger than almost any other objects in the cosmos. A star like our Sun has a lifespan measured in billions of years. But a star like P Cygni is doomed to live only a few million years at best, a blink in cosmic terms. Yet within that brief span, they undergo incredibly complex changes, transforming from hot main sequence beacons into unstable giants and ultimately, into some of the most energetic phenomena in the universe. The problem is, these transformations are rapid, chaotic, and difficult to catch in real time. That's what makes P Cygni so valuable. We're seeing it right in the midst of a rarely observed transitional phase. This phase is the luminous blue variable stage, one of the most unstable and least understood periods in a massive star's life. The LBV phase represents a crucial step between two better understood stages: the main sequence phase, where hydrogen fusion dominates, and the Wolf-Rayet phase, where the star has shed its hydrogen envelope and is fusing heavier elements in a stripped-down, rapidly evolving core. LBVs like P Cygni help bridge that gap by offering a glimpse at how stars transition between stability and instability, and how mass loss during this phase influences the star's destiny. What we observe in P Cygni, the tremendous stellar winds, the periodic outbursts, the long-term variability, the expanding gas shells, all help decode the physical mechanisms behind stellar mass loss, one of the most important and still murky aspects of stellar evolution. The sheer rate at which it loses mass, even outside major eruptions, is a key clue. We know that mass determines the fate of a star, whether it will explode as a supernova, collapse into a black hole, or fade into obscurity. But mass isn't constant. The outer layers of a star like P Cygni are in a constant state of erosion, carried away by the pressure of radiation, the momentum of escaping particles, and the structural instabilities that come with extreme internal heat. By studying these processes in P Cygni, astronomers can refine models of stellar evolution, calculating more accurate lifespans, predicting when eruptions may occur, and determining how much mass needs to be lost for a star to make the leap to the next stage. P Cygni helps constrain the onset and duration of the LBV phase, which for decades has been one of the most mysterious parts of the life cycle of massive stars. Are LBVs inevitable for all massive stars? Or are they a rare exception caused by specific combinations of mass, rotation, metallicity, and internal mixing? P Cygni is one of the few available test cases. Moreover, P Cygni is helping astronomers understand nonlinear stellar processes, the chaotic feedback loops that form when radiation pressure interacts with opacity, when gravity competes with photon momentum, and when thermal pulses destabilize entire layers of stellar atmosphere. The irregularities in its wind velocity, the complex line profiles in its spectrum, the historical outbursts from the 1600s, all of these are part of an unfolding narrative that tells us stars are not machines. They are chaotic, layered, dynamic beings, and sometimes they rebel against equilibrium in spectacular ways. P Cygni also helps astronomers study stellar envelope dynamics in an era before the final collapse. Long before a supernova, a star begins to show signs of structural instability. The radiation flux in the inner layers increases, the convective zones become more turbulent, and the outer layers begin to detach and drift away. P Cygni offers a long-term view of this process, something few other stars provide. And because it hasn't gone supernova yet, We can study it without the obscuring aftermath of an explosion, which makes P Cygni one of the clearest views into a late-stage, pre-supernova stellar interior. Additionally, P Cygni teaches us about feedback into the galactic environment. Every time it sheds mass, whether through its winds or past eruptions, it enriches the interstellar medium with heavier elements like nitrogen and helium. These elements go on to form new stars, planets, and potentially life itself. This cycle of death and rebirth is one of the driving engines of galactic chemistry, and LBVs are among the most efficient contributors. By tracking the abundances of elements in the nebula around P Cygni, astronomers gain insights into how the heavy elements necessary for life are distributed through space. But perhaps most importantly, P Cygni helps us connect the dots between observational astrophysics and theoretical models. It's a star we can actually watch change over decades, even centuries. It's a living example, rather than a post-mortem puzzle like most supernova remnants. With the right instruments, we can monitor changes in its wind structure, surface temperature, and spectral lines, and test our predictions about stellar evolution in real time. In the broader view, stars like P Cygni are also cosmic archetypes. When we observe other galaxies, especially in the early universe, we detect superluminous stars and transient phenomena that we cannot always explain. By studying P Cygni up close, we build the reference models needed to interpret these distant and more extreme systems. Its behavior, quiet now, but volatile in its past, may mirror what is happening in galaxies thousands of light years away. So while P Cygni is just one star, it represents the lifespan of many. It offers a rare and detailed record of what happens when a massive star approaches its breaking point, but hasn't quite shattered. And in doing so, it helps decode the broader mystery of how the universe evolves from simple hydrogen clouds into complex systems filled with metals, dust, stars, planets, and eventually observers like us. Though we often think of stars as points of radiant light, their legacy extends far beyond what our eyes can see. In the case of P Cygni, its light is only one part of the story. Just as important, perhaps even more so, is the material it expels, a steady stream of atoms, molecules, and microscopic grains of cosmic dust drifting into the void. With every breath of its stellar wind, with every shell shed and outburst, P Cygni contributes to the enrichment of the interstellar medium, ISM, the vast, sparse space between the stars that acts as the cradle for new generations of stars and planets. It is in this silent, dusty afterglow of a massive star's life that we find the raw ingredients for everything from planetary systems to the complex chemistry of life itself. The process by which stars like P Cygni enrich the ISM is both subtle and profound. Deep in its core, P Cygni fuses hydrogen into helium, and in later stages, it will fuse helium into heavier elements like carbon, nitrogen, and oxygen. While these reactions take place far from view, the star's unstable outer layers ensure that much of what is synthesized inside eventually finds its way into the surrounding space. The powerful stellar winds, blowing at speeds exceeding 200 kilometers per second, carry mass away from the star continuously. These outflows are not uniform. They form dense clumps, arcs, and shells, some of which have been observed in exquisite detail using advanced telescopes and imaging techniques. Within these winds and ejected shells, dust forms, but not just any dust. This is cosmic dust, forged in the extreme environments of a star that is among the hottest and most luminous in the galaxy. The dust grains that condense in P Cygni's outer layers are made of silicates, carbon-rich molecules, aluminum oxides, and other refractory materials, substances that can withstand high temperatures and later act as the building blocks of planetary systems. These dust particles are incredibly small, often on the order of micrometers or less, yet collectively, they form massive clouds that slowly expand into the ISM over thousands of years. The evidence for this dust lies all around P Cygni. Infrared observations have revealed a faint, extended nebula composed of gas and dust from past eruptions, including the massive event that occurred in the 1600s. This nebula is not as dramatic as the homunculus nebula around Eta Carinae, but it is a testament to the cumulative effect of steady mass loss over centuries. Within this cloud are trace signatures of nitrogen enrichment, a chemical fingerprint of nuclear fusion products dredged up from the star's interior and expelled into space. These elements will, in time, mix with the broader galactic medium, changing its composition and making it more chemically rich. Why does this matter? Because the ISM is the birthplace of stars and planets. As dust and gas accumulate in molecular clouds, they begin to collapse under their own gravity, forming protostars surrounded by spinning disks of matter. The dust expelled by stars like P Cygni becomes part of these disks, seed material for the rocky planets, comets, and even organic molecules that may one day support life. Without the chemical contributions of massive stars, the universe would be a far simpler place, dark hydrogen clouds with few of the elements necessary for complexity. But it's not just about what elements are expelled, it's also about how they are distributed. P Cygni stellar winds carve out cavities and bubbles in the surrounding interstellar material, pushing and compressing gas and dust into new configurations. This shaping of the ISM can trigger new star formation, as the compressed material reaches the densities necessary to collapse into new stars. In this way, P Cygni is not just a passive donor of elements, it's an active architect of the galactic ecosystem. It helps mold the very environment in which future stars will be born. Even more intriguingly, P Cygni and stars like it contribute to interstellar extinction, the dimming and reddening of starlight as it passes through clouds of dust. The dust grains absorb and scatter visible light, reshaping our view of the cosmos. While this might sound like a nuisance for astronomers, it's actually another crucial piece of the puzzle. By analyzing how starlight is altered by dust from stars like P Cygni, researchers can measure the composition, density, and temperature of interstellar dust, learning more about the life cycles of galaxies and the evolution of matter itself. Furthermore, the dust produced by P Cygni isn't uniformly ejected. Observations suggest that clumping and asymmetries in the wind structure may lead to directional outflows, potentially shaping bipolar or multipolar nebulae in the future. While P Cygni's current nebula appears roughly spherical, deeper imaging and long-term monitoring may eventually reveal hidden complexity, evidence of turbulence and rotation that influences how and where dust is released. From a chemical perspective, the dust P Cygni leaves behind carries the signature of nucleosynthesis, the creation of elements in the hearts of stars. Some of the grains it produces are presolar grains, ancient particles that survive long after their parent star has died. These grains can travel vast distances, eventually becoming trapped in newly formed meteorites. In fact, some of the grains found in meteorites on Earth are believed to have originated from massive stars that lived and died billions of years ago, stars not unlike P Cygni. In this sense, the dust it expels may one day be found on the surface of alien worlds, or even incorporated into the body of a living organism. There is a poetic irony in this. A star that lives such a violent, brief life still finds a way to leave something enduring, tiny, persistent particles scattered across the galaxy. And these particles carry within them the story of P Cygni's life, the imprint of its temperature, its composition, and its final struggles against gravitational collapse. The dust of P Cygni is not just ash, it's memory, legacy, and potential. It is the seed of everything that comes next. Though the light of P Cygni itself commands attention, burning bright against the fabric of the Cygnus constellation, it is what surrounds the star that holds some of its most revealing secrets. Encircling this luminous blue variable is a vast, faint, and ghostly shell of material, a nebula, the fragile remnant of ancient outbursts, expanding outward like a cosmic ripple frozen in time. Unlike the flamboyant homunculus nebula of Eta Carinae or the colorful planetary nebulae dotting the night sky, the nebula around P Cygni is subtle and elusive, an almost transparent whisper of the star's eruptive past. And yet, within that whisper lies a vital story. This nebulosity, invisible to the naked eye and difficult to detect even with powerful telescopes, is composed of gas and dust that P Cygni ejected during previous mass loss events, primarily the historic eruption around 1600 AD, but possibly even earlier ones. It has been observed and mapped primarily through narrow-band imaging techniques that isolate specific emission lines, such as those from ionized hydrogen, H-alpha, oxygen, and nitrogen. These observations reveal an extended envelope of expanding material, glowing faintly due to excitation by the star's intense radiation. What we find in this nebula is not a smooth, symmetrical shell but a complex structure, marked by clumps, filaments, and arcs that speak to the chaotic forces that shaped it. The material is moving outward at speeds of 30 to 50 kilometers per second, and estimates of the nebula's radius suggest it has expanded over hundreds of years, consistent with the timing of the 17th century outburst. Some parts of the nebula may have originated even earlier, indicating that P Cygni has undergone multiple eruptive phases in its recent history. The nebula itself is relatively small in angular size, just a few arcseconds across as seen from Earth. But at P Cygni's estimated distance of around 5,700 light-years, this translates to a physical size of nearly 0.2 light-years in diameter. It is composed largely of ionized hydrogen gas, with traces of heavier elements such as nitrogen and sulfur, which appear more prominently in spectral studies. The presence of enhanced nitrogen abundances in particular is a clear signal of cyano-cycle fusion material that was dredged up from the star's interior and expelled, evidence that P Cygni has already exposed deeper layers of its stellar structure to the universe. The nebula's shape tells us even more. While roughly spherical in early observations, high-resolution imaging has revealed asymmetries and directional outflows, hinting at episodic, uneven ejections rather than a single uniform explosion. These features may result from stellar rotation, magnetic fields, or non-radial pulsations, all of which can cause localized mass ejections rather than smooth, global ones. The complex morphology of the nebula suggests that P Cygni's behavior during outbursts is neither simple nor fully understood. Each eruption may involve different mechanisms, geometries, and instabilities. Another fascinating aspect is the nebula's interaction with the surrounding interstellar medium. As the expanding shell moves outward, it encounters ambient gas and dust, creating shock fronts and regions of enhanced emission. These interactions can slow the nebula's expansion and trigger further chemical reactions, creating new molecules and possibly dust grains in the wake of the original outburst. In this way, the nebula is not just a passive remnant, it's actively evolving, sculpting and enriching its local environment. Additionally, the nebula plays an essential role in understanding P Cygni's mass loss history. By analyzing the velocity, composition, and structure of the gas and dust within it, astronomers can reconstruct a timeline of past eruptions. It serves as a kind of astronomical diary, recording the star's convulsions and recovery phases over centuries. This helps refine theoretical models of LBV evolution, especially concerning how frequently such stars erupt, how much mass is lost during each event, and how the geometry of those ejections changes over time. In recent years, technological advancements have enabled even deeper exploration. Infrared and submillimeter observations, particularly from space telescopes like Spitzer and Herschel, have begun to reveal cooler components of the nebula, including cold dust that doesn't emit invisible light. These observations suggest that significant amounts of material may still lie hidden, waiting to be uncovered by instruments sensitive to longer wavelengths. Future observations with the James Webb Space Telescope may be able to pierce the veil even further, offering unparalleled resolution and sensitivity that could redefine our understanding of the structure and composition of the nebula. Moreover, this faint nebulosity is part of a larger narrative, that of stellar feedback and galactic ecology. The nebula is not isolated, it is embedded in the broader Cygnus region, a part of the Milky Way rich in molecular clouds and star-forming regions. The material expelled by P Cygni may eventually merge with these clouds, contributing chemically enriched matter that could one day help form new stars and planetary systems. It's a cosmic cycle of death and rebirth, with P Cygni's nebula serving as one of the early, visible steps in that transformation. In poetic terms, this dusty shell is P Cygni's echo, a lingering footprint of its turmoil, stretched thin across the void. It's the visible memory of stellar agony, a fragile veil that catches starlight and re-radiates it back to the universe. Through it, we don't just learn about what P Cygni was, but what it did, and what it may do again. Before the concept of a luminous blue variable, LBV, had a formal name, before astronomers had even begun to understand the chaotic lives of the most massive stars, there was P Cygni. In a very real sense, P Cygni didn't just belong to a category. It helped create it. Long before terms like LBV or giant eruption were etched into astrophysical literature, this singular star was puzzling observers, misbehaving in ways that defied the established paradigms of stellar evolution. It shone erratically, expelled matter furiously, and glowed with a spectrum that carried an unmistakable and entirely unique fingerprint. Its bizarre behavior demanded explanation. And so, in trying to understand P Cygni, astronomers were forced to broaden the definitions of what stars could be. Historically, variable stars had been known for some time, but most fell into categories defined by regularity, like Cepheids or eclipsing binaries, stars that followed a dependable rhythm or pattern. P Cygni disrupted that idea completely. Its eruption in 1600, visible even to the naked eye, was a shocking phenomenon. A star that had once been faint suddenly increased in brightness and then faded, without any obvious external cause. It wasn't orbiting another star that could be seen. It wasn't exploding in a final supernova. It was something else, something altogether rarer. In the centuries that followed, P Cygni continued to display strange characteristics: irregular mass loss, a luminous and hot surface, and above all, a spectrum that defied expectations. The now famous P Cygni profile, a combination of blue-shifted absorption and red-shifted emission lines in its spectrum, became a hallmark of stellar winds and outflows. This spectral signature was so distinctive and so closely associated with the star that it became not only a diagnostic tool for identifying similar phenomena in other stars, but also a defining feature of what would later be called the LBV phase. When other stars like Eta Carinae and AG Carinae began showing comparable patterns, gigantic outbursts, violent winds, and temporary increases in brightness, astronomers began connecting the dots. These stars were not random exceptions. They represented a particular evolutionary phase, a moment in the life of a very massive star when it becomes highly unstable, begins to shed enormous amounts of mass, and flirts with the Eddington limit, the point at which radiation pressure is so intense that it counteracts gravity. That phase was finally given a name, the luminous blue variable stage, and P Cygni was placed at its heart, not just as a member, but as a model. Unlike many LBVs that were discovered much later, P Cygni's value lies in its long observational record. For over 400 years, humans have been watching it, documenting its brightness changes, studying its wind behavior, mapping its surrounding nebula, and tracking its spectral features. This extraordinary baseline of data gives astronomers a unique longitudinal view of how an LBV behaves over centuries, rather than mere decades. It allows for the development and testing of theoretical models that are not just snapshots but time-lapse sequences of stellar evolution in action. The star also helped redefine what stability means for a massive star. Its variability was unlike that of pulsating stars or rotating binaries. It was driven by internal chaos, radiation pressure overcoming gravitational binding, outer envelope instabilities, and feedback between fusion processes and envelope expansion. This helped astronomers develop a more nuanced view of massive star life cycles, one that included stages of explosive instability between well-understood phases like the main sequence and the Wolf-Rayet stage. Moreover, P Cygni has played a role in expanding the vocabulary of spectroscopy itself. Its unique profile wasn't just a curiosity, it became a standard reference. When astronomers today observe stellar spectra and identify a P Cygni profile, they are seeing not just an abstract phenomenon, but a direct physical connection to this star, material being ejected from a stellar surface at high velocity, creating a dip in absorption at the front and an emission bump from behind. The naming of this feature permanently enshrined the star in the methodological toolkit of astronomy. Beyond spectroscopy, P Cygni redefined categories by showing that massive stars don't evolve quietly. The classical picture of stellar evolution once assumed that massive stars burned through their fuel, gradually expanded into red supergiants, and exploded as supernovae. P Cygni forced scientists to acknowledge that there are intermediate, violent stages, periods of eruption, reconfiguration, and sudden instability that interrupt this process. These interruptions matter because they change the star's mass, chemical makeup, rotation rate, and even its eventual fate. P Cygni thus helped rewrite the evolutionary track for high-mass stars, filling in the missing chapters that had previously been glossed over. It also contributed to our understanding of how stellar feedback operates in galaxies. The mass loss from LBVs like P Cygni feeds the interstellar medium with both material and momentum, sculpting nearby molecular clouds, triggering new waves of star formation, and altering the balance of gas and dust in the galactic ecosystem. Without P Cygni's example, the importance of LBVs in galactic chemical evolution may have been overlooked. In modern astrophysics, the term LBV carries with it a weight of physical implications: instability, variability, mass loss, wind-driven spectra, and a nebular legacy. All of these traits trace directly back to P Cygni. It is not merely one example among many, it is the prototypical LBV, a standard against which others are still measured. In short, P Cygni didn't just fit into a category. It forced the creation of one. It opened a new branch of stellar taxonomy, redefined how we think about variability, and became a cornerstone of high-mass stellar physics. Every time an astronomer speaks of luminous blue variables, every time an LBV is identified in another galaxy, the shadow of P Cygni is there, casting light not just through space, but across the conceptual framework of modern astrophysics itself. More than 4 centuries have passed since P Cygni first erupted into human awareness, a flare in the night that startled early astronomers and forced them to reconsider what a star could be. Yet despite the centuries, despite the vast advances in observational astronomy, spectroscopy, and stellar modeling, P Cygni still matters. In fact, it matters now more than ever. As astrophysics becomes increasingly sophisticated, the kinds of questions we ask about stars grow deeper, more nuanced, and more entangled with the mysteries of stellar life cycles, supernova mechanics, and galactic evolution. And P Cygni, positioned as it is in a rare and turbulent phase of its life, remains one of the few stars that can directly answer these questions, if we know how to listen. The most fundamental reason P Cygni remains a crucial object of study is that it provides a real-time, observable laboratory for examining a phase of stellar evolution that is both rapid and rare, the luminous blue variable, LBV phase. Massive stars spend millions of years on the main sequence, quietly fusing hydrogen into helium, and just a few 100,000, or even fewer, in the LBV phase. In galactic terms, it's a blink. That means that catching a star in this stage is like photographing lightning, difficult, time-sensitive, and incredibly valuable. Most LBVs are discovered because they erupt dramatically, often only once, and then retreat into relative obscurity or explode altogether. P Cygni, by contrast, is persistently unstable. Its relatively continuous activity, winds, eruptions, changes in brightness and spectral features, allows scientists to monitor LBV behavior in dynamic, evolving detail. It is especially important because it occupies a kind of intermediate niche between stars like Eta Carinae, which is wildly eruptive and extremely massive, and more subtle LBVs like Ag Carinae, which show gentler variability. P Cygni exists in a state of simmering instability, not quite calm, but not catastrophic. This makes it a perfect candidate for longitudinal studies of mass loss, envelope dynamics, and pre-supernova evolution. It bridges the extremes and in doing so, helps calibrate our understanding of both ends of the LBV spectrum. Modern observatories use P Cygni as a benchmark, a standard against which new or suspected LBVs are measured. This is because it is relatively close to Earth, about 5,700 to 6,000 light-years away, and its spectral features are well resolved across many wavelengths. We know how it behaves in visible light, ultraviolet, infrared, and even radio. Each observational window opens a different layer of understanding. For instance, its optical spectrum reveals wind velocities and surface temperatures, while infrared studies show us dust production and cool ejected gas, and radio telescopes track ionized wind structures expanding outward. By coordinating these datasets across decades, astronomers are piecing together a remarkably detailed model of how a star like P Cygni breathes, loses mass, and interacts with its surroundings. One reason it continues to matter is because of its stability within instability. That paradox, of a star that is unstable by definition, but stable in its observables, makes P Cygni ideal for testing long-term predictions about massive star behavior. It gives us a base state. For stars like Eta Carinae, which undergo massive, destructive outbursts, observations are often complicated by dynamic dust obscuration and irregular variability. But P Cygni, while certainly active, allows for precise, repeated measurements over long spans of time. This lets researchers test hydrodynamic models of stellar winds and envelope inflation, predictions about line-driven instabilities, and theories about envelope opacity changes and internal pulsations. Furthermore, its spectrum remains one of the clearest and cleanest examples of a stellar wind-driven outflow. The P Cygni profile, so iconic that it bears the star's name, is used in countless areas of astrophysics, from modeling outflows in massive stars and quasars to interpreting gamma-ray burst progenitors. Because the shape of the profile is influenced by wind speed, density, and temperature, P Cygni acts as a kind of cosmic barometer. Subtle changes in its line profiles allow researchers to back-calculate changes in wind structure, acceleration zones, and even the impact of clumping or turbulence in the wind itself. These are critical inputs for theoretical models of massive star evolution, especially in the post-main sequence phase. In fact, many of the questions we still struggle with in stellar physics revolve around mass loss. When it occurs, how much is lost, and how that affects the star's core and outer envelope. Mass loss doesn't just affect the surface, it redefines the future of the star. A star that sheds enough mass may avoid becoming a red supergiant altogether, and instead transition into a Wolf-Rayet star before ending in a stripped envelope supernova. Others may collapse into black holes quietly, without a visible explosion. P Cygni allows researchers to study the cumulative impact of both continuous wind-driven mass loss and discrete eruptive events. These processes directly feed into models that predict supernova types, black hole formation rates, and even the conditions needed for gamma-ray bursts. Moreover, P Cygni isn't just an object of solitary interest. It plays a role in understanding stellar populations in distant galaxies. When we observe luminous, eruptive stars in other galaxies, often at great distances and under limited resolution, we need template models to interpret what we're seeing. P Cygni serves as such a model. Its light curve, spectra, wind properties, and variability patterns are used to train algorithms and calibrate simulations for detecting and classifying transient phenomena across the cosmos. As observatories like the RAREST, Rubin Observatory come online, detecting hundreds of thousands of new transients each year, the need for reliable, well-studied templates like P Cygni will become even more vital. P Cygni also remains a test case for multi-wavelength synergies in modern astronomy. Observations with the Hubble Space Telescope have mapped its wind structure and ultraviolet light. Infrared observatories like Spitzer and Herschel have revealed the cooler, older ejecta forming a faint circumstellar shell. Ground-based radio interferometry has begun to detect the extended ionized regions that trace the reach of the star's influence. And now, with the advent of the James Webb Space Telescope, JWST, we stand on the brink of examining P Cygni with unprecedented resolution in the infrared. JWST's ability to resolve dusty structures, molecule-rich zones, and temperature gradients in the surrounding nebula will unlock new secrets, perhaps detecting mass loss structures too faint or too cold to observe before. Beyond its astrophysical importance, P Cygni also matters as a historical anchor. Its eruption in 1600 is one of the earliest documented examples of stellar variability. Its reappearance and fading helped fuel early debates about the permanence of the heavens, a direct challenge to the Aristotelian view that stars were immutable. In this sense, P Cygni played a role not just in the development of astrophysics, but in the evolution of scientific thought. It is a bridge between early observational astronomy and the high-precision, high-theory era of today. Its name echoes through time, appearing in centuries of scientific literature, linking the past with the present. In education and public outreach, P Cygni continues to captivate. It is beautiful and mysterious, offering a vivid example of how stars can live dramatic lives full of convulsion, violence, and rebirth. It helps humanize the cosmos, reminding us that stars are not mere points of light, but entities undergoing incredible, sometimes tragic transformations. For students and the public, it's a gateway into deeper inquiry. Why does it erupt? What are stellar winds? How do stars die? P Cygni is a starting point for curiosity, a luminous invitation to explore the lives of stars. And finally, P Cygni remains important because it reminds us that our story is linked to stars like it. The elements that make up our world, carbon, nitrogen, oxygen, and beyond, were forged in the hearts of massive stars and hurled into space by events just like the ones we observe in P Cygni. It is not just a star in Cygnus. It is a participant in the cosmic cycle of creation, a window into the processes that make life possible. In a universe filled with billions of stars, most quietly burning or long dead, P Cygni still pulses, still evolves, still teaches, still matters. To truly understand a star like P Cygni, one must abandon the notion that vision alone is sufficient. What the human eye perceives, brilliant, blue-white light shimmering in the Cygnus constellation, is only a tiny sliver of the reality. Stars like P Cygni are multidimensional phenomena, emitting radiation across the entire electromagnetic spectrum. From long radio waves to the shortest X-rays, every part of the spectrum tells a different story about the star's nature, its wind dynamics, its inner workings, and its interaction with the surrounding cosmos. Multi-wavelength observations are not just a bonus in stellar astrophysics, they are essential. Without them, P Cygni would be a puzzle missing most of its pieces. At the visible light level, P Cygni has been watched for centuries. Optical telescopes track its brightness, which appears relatively stable now compared to its 17th century outbursts, but which continues to show subtle changes over time. It is through visible light that the iconic P Cygni profile was first observed, those distinctive spectral lines that combine blue-shifted absorption and red-shifted emission, a telltale sign of massive stellar winds. High-resolution spectroscopy in visible wavelengths continues to refine our knowledge of its surface temperature, the speed of its outflows, and the presence of clumped material in its wind. But visible light alone cannot tell the full story. Much of P Cygni's behavior is hidden in wavelengths either too long or too short for our eyes. For instance, in the ultraviolet UV part of the spectrum, observable only from space-based telescopes like the Hubble Space Telescope, JWST, we peer into a more energetic, volatile layer of the star's activity. Here, we observe highly ionized atoms like silicon, carbon, and nitrogen being accelerated by the intense radiation pressure of the star. The UV spectrum reveals even faster wind components than seen in visible light, sometimes clocked at speeds exceeding 200 km per second, and occasionally showing turbulent shifts that indicate instabilities in the outflowing wind. UV observations also let us study the ionization structure of P Cygni's surrounding nebula and circumstellar shell. This tells astronomers not only how much material has been ejected but also how far it's been ionized by the star's radiation. It's through UV imaging and spectroscopy that we first confirmed that past eruptions had filled the surrounding space with chemically enriched gas, a kind of ghostly halo still reacting to the parent star's energy centuries later. Shifting into the infrared IR part of the spectrum opens an entirely new layer of understanding. While visible light reveals hot gas and UV reveals ionized particles, IR light is where we find the cooler components, especially dust. As P Cygni expels material, much of it cools and condenses into tiny solid grains, which then glow faintly in the infrared. Telescopes like Spitzer, Herschel, and ground-based IR observatories have been critical in mapping this cooler envelope, which extends far beyond what is visible in optical light. These observations have allowed astronomers to reconstruct the size, shape, and temperature of P Cygni's faint surrounding nebula, composed of dust and molecular gas from previous eruptions. In particular, infrared data show evidence of warm silicates and possibly amorphous carbon dust forming in dense clumps or shells. These components absorb stellar radiation and re-radiated in the IR, creating thermal fingerprints that let astronomers estimate mass loss rates, dust production efficiency, and the chemical makeup of the star's expelled layers. Some IR studies even suggest the possibility of episodic dust formation, hinting that small-scale ejections or pulsations continue to sculpt the circumstellar environment even today. Moving even further along the spectrum into the radio and submillimeter wavelengths, we enter the realm of ionized gas and cold molecular clouds. Observations using radio interferometers like the Very Large Array, VLA, or the Atacama Large Millimeter/Submillimeter Array, ALMA, have begun to detect free emission, light produced when charged particles scatter without capturing each other, in the extended wind and outer nebula. These radio emissions provide an independent method of calculating mass loss rates, especially for material too diffuse or cold to emit in the optical, or UV. What's more, radio studies can map the geometry of the outer ejecta, revealing asymmetries or directional outflows not visible at shorter wavelengths. This helps piece together the mass ejection history of the star, how many major outbursts occurred, in which directions mass was flung, and how the material is expanding today. By combining this data with proper motion studies and 3D modeling, astronomers reconstruct a time-lapse of stellar mass loss, giving us a more complete view of how P Cygni has evolved since its 1600 eruption. But perhaps most tantalizing are the observations in the X-ray part of the spectrum. Although P Cygni is not currently a strong X-ray emitter, its category, luminous blue variables, is known to occasionally produce soft X-rays from shocks and colliding winds or sudden mass ejections. These X-rays are typically faint, but their detection can be crucial. They reveal high-energy physics at play, gas being heated to millions of degrees, collisions between fast and slow wind streams, and instabilities in the outer layers of the star's photosphere. Instruments aboard satellites like Chandra and XMM Newton have searched for, and in some cases detected, faint, variable X-ray emissions from P Cygni, suggesting that internal shocks may still be occurring as different wind velocities interact. The X-ray emissions also serve as a litmus test for magnetic activity, which, while not fully understood in massive stars, may play a role in channeling wind flow and producing localized mass ejections. If P Cygni's X-ray signature strengthens in the future, it might hint at deep-seated magnetic dynamics, a hidden mechanism driving some of its variability. Looking forward, multi-wavelength synergy remains critical. With JWST now active, the infrared component of P Cygni's behavior can be studied with unprecedented sensitivity and resolution. Coupled with continued UV observations from HST, as long as it remains operational, and X-ray data from new missions like XRISM, we are entering a golden age of cross-spectrum stellar archaeology. Researchers can now correlate changes in the UV wind profile with dust emission in the IR, or tie small optical brightening events to shifts in radio structure, all in the pursuit of a complete, cohesive model of a star living on the edge of chaos. This cross-spectrum approach also prepares us for what may be P Cygni's final act. If and when it does go supernova, having full-spectrum data from its pre-explosion life will allow astronomers to trace exactly what kind of progenitor it was, how its outer layers evolved, and which processes led up to its collapse. Few stars have ever been so well documented across so many wavelengths, and that legacy will be invaluable when the final light from P Cygni reaches us, whether tomorrow or 10,000 years from now. In this way, studying P Cygni from visible light to X-rays is not just about building a better picture. It's about telling the whole story, from the hot brilliance of its photosphere to the cold dust drifting in its nebula, from ancient shells of hydrogen to the faint whisper of X-rays that might signal a storm beneath the surface. Across the spectrum, P Cygni speaks in many voices, and only by listening to them all can we begin to grasp the full magnitude of its tale. With the launch of the James Webb Space Telescope, JWST, a new era of astronomy has begun, one that doesn't just promise sharper views or longer reaches, but fundamentally different kinds of insight. For a star like P Cygni, which has already revealed so much through centuries of observation, JWST offers a powerful opportunity to dig even deeper into its hidden layers, its internal structure, and the faintest traces of its eruptive past. The telescope's cutting-edge infrared sensitivity and spatial resolution will allow astronomers to look past the glare, past the hot, searing light of its photosphere, and into the cooler, denser regions surrounding it, perhaps even into the dynamics of its deepest instabilities. P Cygni emits most of its visible radiation from the outer layers of its swollen, unstable photosphere. But JWST, operating primarily in the near and mid-infrared, will excel at detecting features that are invisible in the optical domain: dust, molecules, faint gas shells, and structural patterns lost in earlier observations due to either resolution limits or atmospheric absorption. In particular, JWST's near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, are likely to revolutionize what we know about the circumstellar environment of P Cygni. One of the most anticipated discoveries JWST may make is the detection of nested shells of ejected material, layers that were perhaps expelled centuries apart, now drifting invisibly in the void. Earlier IR telescopes like Spitzer hinted at such structures, but their resolution was insufficient to resolve the fine architecture of these shells. With MIRI, JWST could isolate cold dust features from multiple epochs, each with a unique temperature and chemical fingerprint, essentially allowing astronomers to reconstruct a three-dimensional time capsule of the star's past mass loss events. We may discover not one, but many semi-transparent rings of ejected gas and dust, each a record of a different upheaval in the star's history. Furthermore, JWST's unmatched sensitivity to dust composition could allow for precise identification of the materials formed during those eruptions. Are the grains mostly silicates, like glassy beads born from oxygen-rich outflows? Or are they rich in carbon compounds, indicating a different chemical regime in P Cygni's atmosphere at the time? Knowing the mineralogy of the dust reveals not just the cooling history of the ejected material, but also the internal fusion processes that preceded it. In essence, the dust tells us what the star was doing inside when it decided to shed part of itself. But JWST's power goes beyond external remnants. With its deep spectroscopy, astronomers will be able to look directly into the wind acceleration zones of the star, regions just above the photosphere where matter is lifted, pushed, and hurled outward by radiation pressure. Observing in specific IR spectral lines, such as those from ionized iron, neon, or sulfur, JWST can trace how wind velocity changes with height, revealing whether P Cygni's winds are clumpy, smooth, turbulent, or stratified. This is crucial to resolving one of the big open questions in massive star physics: whether stellar winds are a steady breeze or a series of chaotic pulses. The answer changes how we calculate total mass loss, which in turn determines whether a star ends its life as a neutron star or collapses directly into a black hole. There's also the intriguing possibility that JWST might identify asymmetries in the outflow, indications that the mass loss is not uniform in all directions. Past ground-based imaging has hinted at lopsidedness in the outer nebula, but lacked the power to resolve it cleanly. JWST may find jets, plumes, or arcs of denser material, suggesting either rotational forces or localized instabilities within the star's envelope. In some cases, such asymmetries could hint at deeper processes such as internal convective patterns, magnetic fields, or even a hidden binary companion subtly influencing P Cygni's evolution. And this raises a thrilling speculation: could JWST help detect signatures of a binary interaction that has thus far remained hidden? Some models suggest that LBVs, especially those with oddly directed outflows or long-lived stability between eruptions, may have faint or compact companions, perhaps a low-mass star or even a compact remnant, that gravitationally shapes the envelope or triggers episodic mass loss. With JWST's precise spectrographs and coronagraphic imaging capabilities, astronomers could search for faint, periodic motions in spectral lines or subtle shifts in surrounding dust that point to tidal effects. While there is no confirmed companion to P Cygni today, even the possibility of one would drastically reshape our understanding of its long-term behavior and stability. Another area where JWST may offer unexpected revelations is in molecular chemistry. While P Cygni is an extremely hot star, some of the outermost layers of its surrounding nebula may have cooled enough to allow for molecular formation. Simple compounds like CO, carbon monoxide, H2O, water, and even more complex molecules like PAHs, polycyclic aromatic hydrocarbons. These molecules emit strongly in the mid-infrared, and their presence would not only be surprising for such a massive star, but also highly informative. They could indicate slow-moving pockets of gas, shielding themselves from radiation, or perhaps hint at conditions in the circumstellar shell conducive to dust aggregation and planet-forming chemistry, albeit at a vast distance and different scale than around solar-type stars. Moreover, JWST's ability to observe time variability means it could detect minute changes in the infrared brightness of the star or its surrounding dust, perhaps correlated with small-scale eruptions or convective instabilities deep within the star. By monitoring P Cygni over time, JWST can construct infrared light curves that, when combined with optical and UV data, give a multi-wavelength heartbeat of the star, a layered pulse of how the star lives, breathes, and changes. Finally, looking beyond JWST, future missions may push the limits of what we can know even further. Projects like the Origin Space Telescope, if launched, could provide colder, deeper observations into the far infrared, capturing emissions from the oldest and most diffuse material expelled during P Cygni's early eruptions, perhaps even remnants we currently don't know exist. And planned X-ray interferometry missions, like the proposed Lynx X-ray Observatory, could refine our knowledge of internal shocks, colliding wind zones, and even detect thermal gradients inside the star's extended atmosphere, giving a kind of thermographic map of its surface activity. As technology advances, so too does our ability to interpret the whispers of the universe. P Cygni is a master of subtlety, a star whose most violent acts are spread thin across time, layered with complexity, wrapped in dust, and spoken in many wavelengths. JWST and its successors hold the key to unraveling this complexity, not just seeing it, but feeling the contours of its instability, tracing its past in exquisite detail, and perhaps glimpsing the flickering shape of its future. In a sense, JWST is not merely looking at P Cygni. It is looking into it. The story of P Cygni is, in many ways, a tale of resistance. It resists categorization, defies predictability, and dances around the edge of destruction without ever quite succumbing. But for all its turbulence, all its glowing eruptions and mass-shedding storms, P Cygni, like every star, is racing toward an end. The laws of stellar evolution offer no mercy, only transformation. And so, we're left with a haunting question that lingers at the edge of every observation, every spectrum, every light curve: what will P Cygni become in the end? Will it vanish into a black hole, implode into a neutron star, or, perhaps, become something stranger still? To approach this question, we must start with the fundamentals: mass. Stellar fate is decided, almost cruelly simply, by how much mass a star is able to hold on to by the time its nuclear fires go out. When P Cygni first formed, it likely boasted a mass somewhere around 30 solar masses, possibly even higher. That's enormous, well above the critical threshold where a star's life is governed not by quiet fusion and graceful aging, but by chaotic instability, violent winds, and an eventual catastrophic demise. Today, P Cygni is estimated to have shed several solar masses through sustained winds and episodic eruptions. Even so, it still retains a core mass significantly higher than 8 solar masses, the minimum required to undergo core collapse and form either a neutron star or black hole. This makes its destiny as a supernova progenitor nearly certain. The only question that remains is what happens next. If P Cygni continues shedding mass over the next tens of thousands of years, and there is every reason to believe it will, then it could eventually reduce its mass to the point where a neutron star becomes a plausible outcome. Neutron stars are the dense, collapsed cores of supernova explosions, often containing 1.4 to 2 solar masses packed into a sphere only 20 kilometers across. These are some of the strangest objects in the universe, stars made entirely of neutrons, where matter is so dense a single teaspoon would weigh billions of tons. If P Cygni loses enough of its outer envelope before the final collapse, its core might end its life in just such a spectacular, dense rebirth. But for that to happen, P Cygni must shed a tremendous amount of material, more than it has already lost, and this is far from guaranteed. The gravitational grip of such a massive star is strong, and although its stellar winds are fierce, they may not be enough to reduce its mass below the neutron star threshold. Indeed, If P Cygni retains a core mass greater than about 2.5 to 3 solar masses when it collapses, no known force in the universe can prevent that core from collapsing into a black hole. A black hole, of course, is not just a dense star, it is the ultimate endgame of gravity, a region of space where matter is compressed into an infinitesimal point, and even light cannot escape. If P Cygni becomes a black hole, it will vanish in one sense, becoming invisible to traditional telescopes. But it will leave behind a dramatic signature, a supernova, perhaps a type I or 2L, that tears through its outer layers in a final, searing exhalation of light and matter. Some researchers go further, suggesting that P Cygni could become something even more exotic, a failed supernova. In this scenario, the star collapses so completely and so quickly that the core forms a black hole without producing a bright explosion. Instead of lighting up the galaxy, P Cygni might simply disappear, an optical vanishing act. The outer layers would fall in, swallowed in silence, and the only hint of the star's death would be the abrupt end of its light. But other possibilities remain. Some models propose that LBVs like P Cygni could undergo a parinstability supernova, a rare and extreme type of explosion that completely unbinds the star without leaving any remnant behind. In this scenario, gamma rays within the core become so energetic that they produce electron-positron pairs, reducing radiation pressure and triggering a sudden collapse followed by runaway fusion. The resulting blast is so powerful that the star is utterly obliterated. No neutron star, no black hole, just an expanding cloud of enriched elements. However, current estimates of P Cygni's mass suggest it falls just short of this regime, making a classic core collapse more likely than total annihilation. Still, even within the framework of standard core collapse scenarios, the exact type of supernova matters. If P Cygni retains a hydrogen-rich envelope at the time of collapse, it could produce a Type 2P or Type 2L supernova, characterized by a plateau or linear decline in brightness. But if it loses much of its hydrogen layer, it may resemble a Type IB or Type IC supernova, like those observed in some stripped envelope massive stars. These types are critical for understanding the diversity of supernovae across the cosmos, and studying P Cygni's evolution over time gives us an invaluable test case for how different evolutionary pathways result in different explosive outcomes. What makes P Cygni's future especially compelling is that its current behavior is not entirely consistent with any one path. Its mass loss is steady, but not extreme. Its winds are strong, but not as violent as Eta Carinae's. Its brightness is relatively stable for an LBV, and yet it shows signs of internal activity that suggest future instability is inevitable. In many ways, P Cygni is teetering on a cosmic edge, with its fate delicately balanced between outcomes. This makes it one of the most scientifically valuable stars in the sky, because whatever it becomes, it will teach us something profound. Should it form a neutron star, future astronomers might one day detect a rapidly spinning pulsar emitting beams of radio waves, or perhaps a magnetar, a neutron star with a magnetic field trillions of times stronger than Earth's. If it becomes a black hole, it could eventually be detected through its interactions with surrounding matter, perhaps pulling in gas from a binary companion, or stirring up the nearby interstellar medium in subtle but detectable ways. Even in death, P Cygni would not go quietly. And what if it becomes something we don't yet have a name for? There are theories, still speculative, about the formation of quark stars, strange stars, or boson stars under extreme gravitational collapse. While none of these scenarios are currently favored for P Cygni, its position near the boundary between known outcomes means that its final state could challenge current models. It could become the star that forces us, once again, to rethink the rules of stellar evolution, just as it did in 1600, when it first flared unexpectedly into the night sky. So what will P Cygni become? A neutron star, spinning silently in the void? A black hole, swallowing light and time? Or something stranger, something new? The answer lies in the future, and in the slow, burning transformation still unfolding within the heart of the star. One day, whether tomorrow or a million years from now, it will reach that threshold. It will collapse. And when it does, the universe will change again, in one more brilliant flash, or in silence. It begins with a shimmer in the northern sky, a speck of light nestled in the graceful wings of Cygnus, just near Deneb, barely perceptible to the untrained eye. But look closer. Peer deeper. Behind that quiet flicker lies a storm of unimaginable magnitude, a star that has been howling across the void for centuries, not with noise, but with light and energy and time itself. This is P Cygni. And it is not just a star. It is a soul. A roaring soul, cast into the sky. P Cygni does not conform. It resists silence, resists serenity. Where others burn calmly, steadily, predictably, it pulses with a heartbeat older than our history. Its every breath is a gale of charged particles. Its every sigh, a gust that strips away its surface in ribbons of glowing plasma. Even now, it remains caught in a struggle, between its own internal pressure and the pull of gravity, between stability and collapse, between life and death. And in that struggle, it shines. To us, it is a beacon of instability, yet it's more than just an unstable sun. It is a storyteller. Through its spectrum, it tells of mass lost to time. Through its nebula, it whispers of ancient eruptions, each shell a verse of its biography written in hydrogen and dust. Through its profile, it speaks a universal language, one so distinct and impactful that even galaxies and quasars now borrow its name. It is, quite literally, a cosmic engine. A furnace of fusion that creates the elements from which planets are built, oceans are filled, and life takes form. Every flare, every burst of wind, every microscopic grain of dust it casts into the void contributes to the interstellar medium, the galaxy's soil. And perhaps one day, billions of years from now, a distant solar system might form around atoms it once hurled into the night. But P Cygni is more than science, more than atoms and plasma and light curves. It is emotion rendered in stellar form. It is drama on a scale too vast for comprehension, yet somehow deeply personal. Because in P Cygni's rage, we see the fragility of even the most powerful things. In its longevity, we see endurance. In its slow transformation, we are reminded of our own, how we change, how we burn, how we live and vanish and return again, in new forms, to the universe. And there is poetry in this, a beauty that transcends numbers. Astronomers speak of P Cygni in data points and spectra, but poets would speak of it in breaths and echoes and the ache of distance. They would say that this is not just a star, but a memory still unfolding. A legacy of light. A cry from the heart of the cosmos that has not stopped reverberating since the first humans looked up and wondered what it was. As telescopes grow stronger and theory stretches further, we will understand P Cygni in ways unimaginable today. We will peel back its layers, trace the paths of its wind-blown tendrils, predict the moment it finally collapses into silence, or explodes into brilliance. And yet, even then, it will remain a mystery, not because we failed to understand it, but because it contains more than facts. It contains wonder. There are many stars in the sky. Most live quiet, noble lives and fade without ceremony. But a few, like P Cygni, rage against the dying of the light. They roar. They rebel. And in doing so, they remind us that the universe is not cold, not indifferent, but full of fire and defiance and meaning. P Cygni burns still, not because it must, but because it can. Because in that burning, it leaves behind a legacy written not on pages, but on the fabric of space and time itself. And when it is gone, when that final outburst comes and its soul becomes one with the dark, we will remember. Not just the light it gave, but the roar it left behind. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.